pleased to have Thorsten Altenkirch as our first speaker, talking about containers and inductive types. So if you could share your screen, Thorsten.
I'm going to share my screen. Hopefully this is the right one. Where is it? Oh, here we are. Okay.
Great. Take it away.
I cannot see. Hang on. I cannot see the. Hang on. I cannot see the chat now. What is this? Is this intended or chat? Oh, here. Okay. Good. Yeah. Good. Good. Whatever time it is. Yes. So I'm going to talk. The title of my talk is. Oops. The title of my talk is. Oops. No, it's not. I think I said container and inductive types. But maybe I should also say container or polynomial. This is longer, by the way, yeah? Did you realize that this is a disadvantage? But anyway, okay. So yeah, let me start with thank the organizers for organizing this workshop and also inviting me. And especially, I think it's a good idea to bring different communities together. So I think we sometimes use different words for the same thing, but I think that's completely okay because it reflects different intuitions we have, different where we come from. And actually, I think adopting a new intuition or adopting a new view on something you know is a bit of a superpower because you can all of a sudden have a different perspective on your problems and on your concepts. So I think that's quite a good thing. Okay, so what am I going to do today? I want to give a bit of a sort of historic overview, to be honest, about my sort of the work on containers, polynomial functors I've been involved in. Is a bit of a specific perspective. So I should also apologize that I may not give always the right references. So I'm really happy if people add something or correct me or give me pointers. Please use the chat also if you want to say something in between. I think that's quite. I mean, I'd rather yeah. But I think something I miss with online meetings is the sort of the interaction, the feedback. And at least via the chat or something like this, we can have a little bit of this. Okay, so my first story is about initial algebras. So maybe here's a question: How do programmers get involved in category theory? And I would say one main source, especially for functional programmers, is the use of category theory to express patterns or in functional programming. And there are a number of very successful patterns which also implemented in terms of libraries. So one of them is Monads for effect, to model effects, computational effects, so things like state update or errors and so on. So they are very successful. But another topic are these initial algebras. Let me just quickly write down what I mean. So having given a functor from set to set. Okay, so what do I mean by set? So I underline it to indicate it's a category. Hence, I'm looking at the morphisms between categories, functors. And sets for me are actually types. So if you press me, I would say these are sort of simple. There are some types whose equality is propositional, whatever this means. So that's something from Hot. So given such a functor, we have a set mu t and a function from t mu t to mu t, which I call it different depending on the day. Let's call it int t. And what's the property? So given any algebra, there is a unique function which we call fold f, which makes this diagram commute. By the way, so in this context, these things are called, this is called a catamorphism. So I mean, it's a shame I cannot do a vote quickly, but I would like to know how many category theoreticians have seen the word catamorphism before. So, okay, I can only see a few people. In Wikipedia, it says is a notion from category theory. Well, maybe that's correct. But I think it's rather specific for this sort of functional programming view of category theory, or the part we are using. So there's also the dual, which are terminal coalgebras, and they can be used to model infinite non-well-founded trees, I think, which have been the subject of Helle's talk to some degree. Okay, and what are generic? I mean, so what we use this for is to express generic patterns. And just to give one example, so-called fusion theorems. So fusion theorems are about the situation when you have a program which first creates a data structure and then immediately consumes it. Then often you can fuse this together and avoid the creation of the data structure. And these are called fusion theorems. And these fusion theorems can be formulated in a way which is generic in terms of data types. Okay, so now I have a dog problem. I don't know what to do about this. But yeah, right, Lambert-Mertens and the Bird-Mertens calculus, that's very true. Okay, so how do we get to containers or polynomial functors? So actually, yeah, let me tell you a little bit of history. In 1999, I wrote a paper with Andreas Abel. By the way, it's quite impressive how I have so many co-authors who come before me alphabetically. I don't know why this happened. You would think with Altenkirch you're pretty safe, right? But no, Abel and later Abbott managed to get before me. Okay. So we were designing a lambda calculus. Okay, when was this? It was 99, the last millennium. We were designing a lambda calculus with inductive and co-inductive types. So no dependency. So you could write things like mu x, let's say 1 plus x plus nat arrow x. And there could be also nested, or you could also use new. So, and you would have obviously this fold or this unfold. And okay, what we didn't want, we only wanted to have strictly positive types. So we didn't want something like mu x, x arrow 2, where 2 is bool, yeah, which is a positive, is a functorial, but not strictly positive. And you may ask, why did we not want them? I mean, one possible reason is that there is no set theoretic. I mean, no classical semantics. It's inconsistent with classical logic, but maybe that could be also a feature as far as I'm concerned. More seriously, it sort of contradicts the sort of intuition how inductive types are sort of created or understood in a process of sort of completion, which corresponds to taking a co-limit. So we wanted to have strict positivity. So not this one. So we wanted to, or we enforced syntactically strict positivity. And then what we wanted to prove is we want to prove a strong normalization theorem. So that all programs terminate basically. And yeah, we were using a modification. I mean, maybe people have heard about Girard's method of candidates of reducibility, and we used a variation of this. But also we didn't want to use impredicativity on the meta level, because it would have been a bit yeah, against our philosophy to do this. So to do this proof, to adopt this Girard proof, we needed okay, I have a problem. Okay, we needed to express the condition of strict positivity semantically. And at this point in time, we used something which is called set-based, so set-based predicates, or was inspired by set-based predicate due to Axel. Okay, so we didn't use containers at the time, but this was the first of inspiration for doing yeah, for having semantic notion which corresponds to the strict positivity. And then I worked together with Neil Garner and Michael Abbott in Leicester. Abbott, I don't never know how to write Abbott, maybe like this, or with two P's. I always had this problem. But anyway, it's another person who comes alphabetically in front of me. So I had to do the long trip from Nottingham to Leicester to work with these guys, and yeah, that was very hard times. We always went for curry and then to the pub after work. It was quite fun. And so we started working out. I mean, they were better in category theory, and I was more into the type theory. So we worked out this idea of a container. So let me just repeat some stuff which I'm sure you have already, which I have already seen, but I want to introduce my notation. So if you have a set S and a family of positions, you can form S triangle P, which is a container, and that's a functor from set to set. So this notation with a triangle sort of expresses this idea that a container has a shape S, a triangle, and down here it has this position P of S where we can plug in some data. Okay, and the meaning in type theoretic terms is very simple. It's just sigma S in S, P of S, arrow X. Yeah. Okay. So examples have been already given. I mean, S could be not, right? And P of N are these finite sets of numbers. And this is then the list container. But more general, we could have here S is some notion of trees, so unlabeled trees, and P of N counts the leaves or counts the nodes, and depending on what you count, you get a leaf labeled or a node labeled tree. We also actually did consider n-array containers, but I don't really want to talk about them, which are first step towards indexed containers, or dependent polynomial functors, which we have seen already. I mean, in our first paper, we proved an observation which was already also mentioned in some other talks, namely that the natural transformation, so let me just write this as an AND, which I find quite nice, fits in with a type theoretic notation. So the natural transformation between two containers are just given by a function on the shapes, and then a family of little s in S P of f of s till Q of f of s till P of s. And the proof, I think, is quite, there's an X missing. The proof is quite nice application of the Yoneda lemma. And actually, we also need this type theoretic axiom of choice. And yeah, the nice thing is actually the following observation. This thing here is large, so it's not a small set because I quantify over all sets, right? Whereas this one here is clearly small, right? So unlike functors over sets, endofunctors over sets, containers have a small Hom set. And this is actually essential to prove that the category of containers is Cartesian closed. And this was actually a paper, some work together with Sam Staten and Paul Levy. Okay, actually I am as well. Because you think you can apply the usual formula for calculating exponentials, but you can't because of the size problem. But as soon as you know that the Hom set is small, then you can actually calculate a small set corresponding to the exponential, and then you have to do some manipulation to see that it's actually a container. And actually, this also shows that container are model. I mean, it doesn't show it, but it's also used in establishing that container a model of type theory, which is actually important for the current work I'm talking. Yeah, I hope to be able to talk about it at the end. Okay, here's another thing which I think was also observed. So what is or already mentioned by Richard, for example. So what is composition of containers? Okay, and let me just give you a diagrammatic construction first of all. So here we have one container, S in S, and down here we plug in, another container, T and T. I mean, there are different T's here, T, and then we have some positions here. So these positions are P of S, and these are given by Q, depending on where we are. Now, what the whole thing is a new container. Okay, let me just write this. So what are the shapes? So the shapes are, so let me just write this down, oops, no, I have the wrong pen. I want to do this pen on the black. So the shapes are a function which gives me for every S a T, okay? So it's a function from S to T, and a shape in T. So it's hang on, yeah, no, hang on, no, I'm wrong. So what am I doing here? No, I'm talking rubbish. Anybody? Okay. So what is it? It's not. It's this shape. It's the shape S in S. And for any position here, I have to assign a shape in T. So it's a function f from P of S to T. So these are the shapes. And what are the positions? The positions are really the sort of path. You have to choose one place here and one place here. So, and that is really triangle is another pair, namely a choice here, a P and P of S, and a Q of F of P. So these are the path, this small path we have here. Now, obviously, you can just calculate this using some type theoretic isomorphisms, but I find it quite handy sometimes just to think about these diagrams. Okay. So that's what I wanted to say about the basic theory of containers. And now I want, what happened now? Oh, sorry. Is everything okay? I just, okay. So what I wanted to talk about next is an application of containers, which is actually due to Conner-McBride, namely derivatives. So that was actually, so the point here is, if you have a new semantics, it gives you a new opportunity to express generic constructions. And the generic construction Connor was looking at is the idea of a zipper. I'm not going to define exactly what this is, but the idea is that you need a data structure with a pointer, with a focus to some point. And that's quite a common ingredient of many constructions in functional programming. And one of the ingredients to define the zipper was the type of one-hole contexts. Okay, what do I mean? Of a given type, okay? So the idea is this: you have a parametric data type, let's say f of x, or x times x, or you also can write it x squared. And how does this look like? It's a box with two positions. Now, if you make a hole in such a box, then there are two ways you can make a hole. You can make a hole on the left and keep the right, or you can make a hole on the right and keep the left. So suggestive notation, the derivative or the type of one-hole context is x plus x, or 2 times x, 2 product x. Okay. So so this story actually continues. So let me give you a visual explanation of the chain rule. So what is the derivative of f compose G? Let's see the both containers. So here we have f, and here we have everywhere these G's. Okay, and what is a data type as a whole? I mean, I can draw it like this. We have a data type, and then there somewhere is a hole in the positions. Now, if you have this composition, there can be a hole somewhere here, right? And how can we construct this from the data we have? Now, yeah, the following idea: I consider f as a whole, but with the same g. So that is derivative. Oh, let's apply it to some x. Derivative of f at g of x. But then I'm also left with this thing here, which is a g with a whole. So it's time derivative of g of x. Okay, maybe like this, more mathematical. So we see, so for me, actually, I find it easier to remember the chain rule by thinking about containers than thinking about differentiable functions, to be honest. So what is the formal definition of the derivative of a container? So what is S triangle P? Now, yeah, it's quite straightforward, because the new position is a pair of the old position and a choice of a position where the hole is. Right, let's call it P. And then the positions are all the positions we had before. Oh, no, it's called Q, which are different from this position. Okay. And actually, if you look at this formula, it's a typification of the usual formula for the derivatives of polynomials, if you think about it. Okay, there's also another possible definition of a derivative. So that's also the same as the Cartesian morphisms of the identity container into the container we are looking at. And here Cartesian means the usual thing, as that the Pullback squares are pullbacks, or alternatively, that's the second component in the morphism. I don't have morphism not too far away. That the part of the morphism on positions is an isomorphism. And it's also not difficult to see why this works, because this I is sort of like a walking hole. We send it somewhere, but we can only send it to one place. We cannot copy it or forget it. So in a way, we have here a linear map. Cartesian morphisms corresponds to linear maps, and maybe it's not too surprising that we need linear maps to define derivatives. I've seen this before somewhere. I don't know. Okay. So now comes in Håkan Hilderud, who wrote a master thesis. He was supervised by Dag Norman in Oslo about what he called symmetric containers. And he was concerned with the question. Oh, I forgot to say something. Yeah. So what is the antiderivative of a container? So the opposite. He didn't say integral because obviously we're not in calculus. But what is the antiderivative? I forgot to say one thing, namely there's also another visual way to describe the derivative. So for example, what is the derivative of a list? So a list can be represented as a sequence, right? And the derivative of a list means that the list with a hole. Now, if you have a sequence and you make a hole in it, you get two sequences. And it's indeed true that the derivative of lists is list times list. And by the way, this you can actually derive just using the chain rule in the multivariate calculus, using the chain rule and sort of a fixed point calculation. You can actually derive this equation. But so the idea is that we can think of derivatives of a list with a hole, so which falls apart to two lists. But Håkan asked the question: is there a container such that the derivative of this container is list? Right. And we see already that's a little bit difficult. I mean, how can we have something and we make a hole in and we get a list, right? Actually, maybe you've got an idea, but we have to generalize the notion of a container, and we have to talk about what he called symmetric container, which is also, we could call it a groupoid container. And I think some people here, I think Joachim, for example, has also worked on this. I don't know who started it when, I have no idea, but I learned it from Håkan. So the idea is that shapes are now groupoid, and the positions are a functor from this groupoid to the category of sets. Right. And what is the semantics? Semantics is again here a functor from set to set. We stick to this, maybe mistakenly, and now I get a coend or a colimit. No, hang on. Hang on. Yep. What am I doing? Yeah, S in S. Sorry. P of S over X. So that's just a colimit, but I quite like to write it in this notation. I think it was Mauro Yaskeliov who finally helped me to overcome the confusion where to put the index for ends and coends by telling me that if it's an end, then the index is close to the end of the whiteboard, and if it's a coend, then it's close to the coend of the whiteboard. So this way I can remember it. Okay. So what's the answer? Or let me first say something else. There is a container, namely a container for multisets. It's a groupoid container. So what is S? So S is a category. So has its objects, natural numbers, and as morphisms. So S, M, N are the bijections between fin, M, fin n. And obviously, this is just a category or the groupoid of finite symmetric groups. And the positions is just P of n is fin n on objects, and on the functions we just apply the permutation. Now it turns, I mean, it's the derivative of this container, so the derivative of multisets is multisets, so it plays the role of the exponential function in calculus. And also there is I think there is a simple sort of graphical argument. If you have like data structure with 4 nodes, and they in the multiset each is connected to all the others, and you take one away, you just get another multiset, one less. So this sort of whole idea works here. But coming back to the antiderivative of lists, they are given by cycles. So here, the object of S are natural numbers again, and Smn are like shifts, right? It's a number I, which is Snn is a number I less than n, and basically we perform this rotation, and these are the finite cyclic groups, groupoid of the finite cyclic groups. So P of n is just fin n again, and the function which is given by a number is just n to n plus I. No, I. What do I do? Not j. Sorry, I plus j modulo n. Okay. So yeah, and there's also an easy geometric idea here. So that's a cycle, and if you take one point out of a cycle, you get a list, right? So that's a sort of geometric, diagrammatic intuition for this. So the antiderivative, so the derivative of cycles are lists. But you may ask further, do all groupoid container now have an antiderivative? And the answer is no. And there's a clever proof by Christian Sattler, namely that a cycle of size n, so not all the cycles, but just a cycle of of size n, so we fix the shape, has an antiderivative if n plus 1 is the size of a finite group, a finite field, sorry, finite field. So it means that this is Christian Sattler. It's unpublished result, and that means in particular that C5 doesn't have an antiderivative. Okay. Yes. Let me say I want to do one remark on this. So the question, for example, and I wonder whether anybody has any comments on this. So yes, species, I should have mentioned it well. Say okay. So so does is a composition of groupoid container a groupoid? And I wonder whether anybody has looked at this, because I think it's equivalent to the axiom of choice, but not the type theoretic one, but the proper one. And I mean, if you look at the definition, then you see that we have not here sigma type as before, but we have actually a colimit, which is a quotient, and moving functions over quotients involves axiom of choice. There's also another definition, equivalent definition, I think it's equivalent, of the group root container. So if you're in homotopy type theory, you can say S is a one type. So it's a one type. A one type is a type whose equalities are sets, and the positions are just a normal function from S to set, let's say. Okay. And then, so what's the container? So we want to still get a function from set to set, and that's maybe already a bad idea. But so if we do this, then yes, we can just form the usual thing, but this is not a set, but this is a one type. So we have to truncate it. Right? And now the problem is that, again, you have to move a function over truncation, and that's an axiom of choice. So I think that I haven't proven it, but I think it's actually, equivalent to the axiom of choice. But I'm quite interested to hear what other people think about this. And yes, so I should have mentioned that there is, we have discovered this and then obviously realized that this is closely related to combinatory species. And I think Marcelo is going to talk about this. It's a bit of a slightly, I would say, different motivation coming from data types and type theory, and also allowing infinitary constructions. But a lot of the stuff is related to combinatory species. Okay, this is not working. Don't know what's going on here. Okay. I have a problem with my cheat sheet. I don't know what's going on. What is this? Okay. Why is this not working? Oh, I know. My iPad was lying on a key. That's bad. Okay, so let's come to my current interest, which is related to, which number is this? Oh, 4, which are higher inductive types, or actually higher inductive types. Inductive types in hot, basically. Okay, so what are higher inductive types? If you look in the hot book, there's one example, is the construction of the Cauchy reals. And the Cauchy reals are here constructed as Cauchy completion of the rational. And this construction avoids the use of the axiom of countable choice to prove that the Cauchy reals are closed under are Cauchy complete. And the idea here is that we, at the same time, we construct the real numbers. So basically, say all the real numbers are all the rational numbers, and any convergence sequence of real numbers gives you a new real number. But we have, at the same time, when we construct the reals, we have to define the equality, and actually we also have to define an order relation. So we do all these things mutually, and this mutuality is I think, one of the main features of this sort of constructions. There was also, we did another construction, or we did similar. We constructed what we call the partiality monad, which is basically, so given a type, you have the type of computations which may diverge. And this is actually the free omega CPO over a given set. Or this was and here we also used a higher inductive type, but actually, to be honest, these higher inductive types are not very high. They are actually rather quotient, I call them quotient inductive types, because these are all sets, right? So these are all, they're not very high. The interesting aspect is that we define several types and the equality at the same time. And it is actually this mutual character. So we say inductive. If we have a situation like this, we inductively define a type A, and at the same time, we define a family indexed over A. So we mutually define a type and a type indexed over it. And when you try to do this, you find you cannot actually get this sort of functorial semantics anymore, because okay, let me give an example. So one example is what we call the intrinsic syntax of type theory, and the point here is that we define, this is syntax of type theory, so we solve the initiality conjecture, but we never define untyped terms. So usually in definition of type theory, or in the last millennium, you first define untyped syntax and then you find a typing relation. But actually we don't need to do this. We can do it all at once. And then you end up with a type. So you define the context and you find the types which are indexed over the context, and you define the terms. Let me just, and substitutions. Substitutions, which are just indexed by two contexts. And then you introduce lots of constructors. So, I mean, for example, you have composition of substitutions identity, and then you have some equations like this one, f composed with it is equal to f. So that's an, call it right. So you have these equations. But maybe to draw the attention about this inductive character is something like this. So you define context extension. So if you have a context gamma and a type over gamma, so then you can build a new context. And now we define pi types. So what's a pi type? Given a context, given a type A in gamma, and given a type B in gamma extended by A, we get a new type in gamma. Okay, and what is the point here is that we actually have this dependency, right? So we first define this constructor, and then this constructor appears in the domain of a later constructor. So this whole idea of now coming up with an endo functor doesn't really work, because one constructor depends. There's like an order in these constructors. One depends on the other. Okay. What happened now? So the question is how to model this, and we did some work on this. This was work with Gabe Dijkstra and Nikolai Kraus and Paolo Capriotti. So the idea is the following. You start with a category of algebras, let's say A0, and we can always use FAM. So what is FAM? FAM is the category whose objects are sets and families over the set, or this is equivalent to set arrow. And then we add the constructor, and we have a new category of algebras, and then we add another constructor, and so on. So we do this really. We construct this category of algebras in stages. And now, what is CI? So that's going from AI. So CI going from AI to AI plus 1 is given So CI is actually a dependent function where you have the left-hand side and the right-hand side, and this X is actually an object in AI. I should have said this. So every constructor is such a dependent function, and what are L and R? L is a functor from AI to Z, and R is a functor from the elements of L to Z. Now, the current work concerns the containerification of this. So obviously, what we need to do is, first of all, we have to understand a container as a pre-sheaf over a given category, with category C, let's say, to Z. And how can we do this? We have S and Z, and P is just a function from S into objects of C. And then the container is a functor from C, a covariant pre-sheaf, so pre-sheaf over C op, if you like, given by this formula. And actually, so most of the constructions I've sketched, they work very nicely also for this notion of container. So now we can say L and R are actually containers, and we can work out what this actually means in detail. Now we have to add some more restrictions on R and on C. So basically that R has the same shapes and L, so this is actually the same shapes, and that C preserves the shapes. Otherwise we're not able to construct initial algebra. Okay, so here, okay, like, can I have I got time? I've almost no time. One remark is that this is also, we can, if you look at indexed containers, they also correspond to pre-sheaves, right? So actually the indexed containers can be understood as defined over this category here. And yes, as was already mentioned, so basically the idea is that a container in this generalized form is just a coproduct of representables. Okay, so this semantics, this container semantics of higher inductive types also leads to a new syntax. And the syntax is basically, we have these sequences of constructors, so starting with the empty sequence, and then we add one constructor, and then we add another constructor, and so on. And over each of these constructors, to be able to construct the left and the right-hand side, lives a model of type theory. So we have a type theory. And here we use the fact that the containers over a given category form a model of type theory. And we need the syntax of this type theory to formulate these left and right-hand sides. So like these things here. This is the left-hand side. This is the left-hand side, right? And this is the right-hand side. So this gives rise to a syntax, and this is I think a refinement of a syntax for quotient inductive types, syntax for QIITs, refinement of the syntax given by Kaposi and Kovac. As a refinement, because actually I noticed that my semantics doesn't work for their syntax. So if you think of the category of algebras, you get a forgetful functor in this direction, and then you have a left adjoint, which is a free extension. And since we can, the important thing is that we can move these containers, which are the models of these types along these forgetful maps, because we have an adjoint. So the conjecture is that this syntax, which I haven't given much details, is complete for the semantics. Okay, so we have a syntax which matches exactly this is, I think, very simple container semantics, but as I say, it's a conjecture. I haven't yet completed this construction. And this syntax, if my conjecture is true, is a universal quotient inductive type, but it's quite a complicated one. So the question is there simple QIIT, or simple type from which we can derive all this? So this is the search for a QW type. I mean, it's like the W types in type theory, and there are some candidates for it, but haven't yet settled on any particular scheme. But I think so. I hope. I mean, I'm leaving some time in the hope that people ask some questions. So I'm basically done.
Okay, thank you, Thorsten. People can now unmute themselves to ask questions,
give comments, or
give comments, etc. I had a quick question while we're waiting. Upstairs, you said the derivative could be defined by the Cartesian maps from the identity.
Yes.
What did you mean? Is that supposed to be? Is that Hom set supposed to be a polynomial, or I mean a container, or?
Yes. So you can calculate. This is a container. So this is a container. This
What
is exactly a container.
What is meant by the container of Cartesian maps from one polynomial to another? Or one container.
Okay, it's a set of natural transformations, Cartesian natural transformation from I to this, right? Did I overlook something?
So that would just be a set, or?
Yes, I a bit confused in the moment. It's a set, but it should be container. So what's the problem?
And there are no Cartesian maps from the identity to the square. Let me see. Whereas we're expecting 2y. So yeah, I just wasn't sure about the formula there.
No, I think I got something wrong here. It's a bit a long time ago. I just thought, yeah.
I mean, I think it's also the case that it happens to be the case that the Cartesian morphisms from the identity to a container are isomorphic to another container.
Yes, that's true.
But one should not expect Cartesian morphisms from this container to that container necessarily given by containers.
Yes. Yeah, I agree. My definition is answered. I'll fix it. So I'll look it up.
So yeah, it happens to be that by figuring out how to stop talking about the whole, those particular Cartesian morphisms are given as containers.
Yes.
But I don't think that's necessarily the general situation.
Yes, so it's exponential. Is it then okay? Maybe it's something like this applied to x, but I really have to check this.
Yeah. I mean, it's also terribly interesting, and let's just plug Fred's talk for tomorrow. What happens when you pay attention to more kind of resource usage issues in this picture? Sometimes.
Yes. Yeah, I think this is a container, and then if we apply this container to X, we get the same. Well, I think that's what it is.
Well, I don't mean to derail you or to prevent others from asking questions.
Yeah.
I can ask you offline also.
Yeah.
Yeah, no, I'll try to look it up in this paper. This is the paper partiality for data, which is based, which is with Neil Garner, Michael Appelt, and Conor McBride. Yeah.
Okay, other questions for Thorsten?
Maybe I can make a comment.
Uh-huh.
So in the theory of species, so there are different versions. In fact, a lot, but one would be species of structures, and the other, they're called linear species.
Uh-huh.
So the linear species are like the containers or the polynomials, and the species of structures are the ones that have this quotient by automorphisms.
Oh, yeah. Mm-hmm.
And in fact, it's known in that theory that there are no antiderivatives in species. Mm-hmm. And in fact, to solve differential equations combinatorially, what they do is they move to the linear setting.
Mm-hmm. Yeah. Okay.
So
we have, I mean,
looking for kind of, one should look for, I think, antiderivatives or solving differential equations really in the linear setting.
Mm-hmm. Yeah, I mean, as I say, I mean, certain antiderivatives do exist, and Hilderud proved that for any normal container, for any not groupoid container, you have an antiderivative which is a groupoid container. But antiderivatives of groupoid containers do sometimes exist, but not always, right?
Yes. Yeah. Yes, so there is no general theorem. That's my point.
Yeah.
Okay, any other questions, or shall we take our 2-minute, let's see, tea break? I guess we have. What I don't remember what we've decided on here, but.
Choose whichever letter of the alphabet you like to characterize the break.
That's right. Well, thanks again, Thorsten.
Okay.
Okay.
What happened now?
Thank you, Tim. High-tech workshop here. Kristina, if you're here, would you want to check your slide sharing ability? I see Kristina in the meeting, but
We're talking to us. Oh, hang on, maybe I should mute myself now.
no problem either way. Ah. You there, Kristina? Your microphone does not appear to be working. Is there a way to call in? We sent I think we sent the meeting. Let's see. So there is a meeting ID and passcode that I'm putting in the chat here. I don't know exactly how that lets you call in, but I think it does. You could also try leaving and coming back.
Hello?
Oh, hello. Yes. Well, certainly better. I'll mute people. Do you want to try again, Kristina?
Okay, is this working?
You might be logged in more than once or something because we're getting an echo, but it's almost working. If you're on more than once, that's the only thing I can think of because you and I are the only two unmuted. Want to try again? Okay, maybe if you maybe you could turn the sound off from your computer or something like that so that we don't get the echo. Or mute yourself on one device or the other.
Okay, how about now?
Oh yeah, that sounds good. And do you want to try sharing your screen?
Yes. Okay, is that working?
Doesn't appear to be yet, no.
I mean, I can, oh, entire screen.
Ah, yes.
Now?
Yep, it looks good. Okay, so without further ado, we're pleased to have Kristina Sojakova talking about initial algebras and homotopy type theory. Please, Kristina.
Okay, thank you. This is happening to me very, very often ever since the pandemic started. So, and I can never figure out why. So, well, thank you for having me, David and Joachim. I'm happy to be talking about initial algebras in homotopy type theory. And, well, this is obviously a math workshop, but I'm officially a computer scientist now. So why do computer scientists like me like initial algebras? Well, we like them because they provide a good semantics for something that is found very often in computer science, namely inductive types, such as numbers, natural numbers, lists, and so on. And as is well known, initial algebras for polynomial endofunctors correspond precisely to such inductive types. And that's why people like me are interested in polynomial functors and inductive types, because then we know that the system that we are programming in actually has a good semantics. And conversely, why do mathematicians like inductive types? Well, on some days I'm also a mathematician. So, well, there are theorems such as, for example, Adamec's theorem that tell us that under some conditions, initial algebras for polynomial functors always exist if the category is well behaved. But it's also useful to have a specific explicit description sometimes of such an initial algebra, and that is precisely what an inductive type provides. And also, why do mathematicians and category theorists care about type theory? Well, because it gives a syntactic way and a much easier way to reason about semantic structures that mathematicians care about, such as fibrations, locally Cartesian closed categories, and so on. So many constructs are carried out using internal languages, which are basically type theories suited for the specific categorical construct we have in mind. So some people think that basically we are all doing the same thing, just from a slightly different perspective. So how do we generally describe inductive types? Well, one way is by using a schema, such as the schemas found, for example, in Koch, where, as Thorsten was mentioning, we have some additional requirements, for example, strict positivity requirement to ensure that the user can't just write something that we don't actually know how to interpret semantically. The other approach is by using, the former is a more computer science-y approach that is a bit more user-friendly. The second one is perhaps less user-friendly, but maybe a bit more elegant type theoretically, because we have one general construction, such as, for example, the type of well-founded trees that we will cover in a bit more detail tonight, also known as W types. The W stands for well-founded, which generalize the usual inductive types, such as trees, lists, and so on, that we encounter on a daily basis. And so we can carry out some kind of argument once and for all for this general construction, and then it kind of carries out automatically for everything that arises as a special instance of such a W type. So what exactly is the relationship between initial algebras and inductive types? Well, in extensional type theory, again, we will talk a bit more about that later, but they are known to coincide. This is, I think, due to Peter de Beer originally. So an initial algebra can be precisely characterized as an inductive type and vice versa. However, when we move to, so again, the extensional type theory is a very, very good, elegant theory to work with on paper. But then when we move to modern proof assistants, most of them implement some version of an intentional type theory as their basis, because that has type theoretic properties that are a bit easier to work with when it comes to semi-automation, for example, such as decidability of type checking. So unfortunately, in this, in the intentional system that underlies most proof assistants nowadays, they do not coincide, because, as we will see later, we don't really have a way of proving that two functions are equal. We can prove that they're pointwise equal, but if the function extensionality is not ordinarily part of the theory, so we don't really have a way of establishing the equality of arrows in a category. So the category that such a theory induces is not a very good one. And in particular, it doesn't satisfy the conditions that, for example, Adamek's theorem requires to guarantee the existence of initial algebras. So that's an intermediate system that's perhaps a bit broken. So there comes homotopy type theory that fixes everything that's wrong with intentional type theory and then some. So that's originally due to many people, but most specifically, the original idea comes from Steve Audi and Michael Warren on one hand, and then independently Voivodsky had insights about univalence that basically showed us how to use some geometric intuition from abstract homotopy theory to design a better type system that we nowadays call homotopy type theory. And the correspondence is restored after we replace initiality in the statement by homotopy initiality, which is the natural form of initiality in the proof relevant setting. So that result, very old already, due to Steve, Nicola, and myself. That was actually my first result in homotopy type theory. So when I was just a baby PhD student. So now we can very briefly go over the type theory that started it all, the extensional type theory due to Martin Löw. So I was told that a lot of people in the audience will have more of a categorical background than a type theoretic one. So I actually made sure to avoid a turnstile, because when I was just in one of my very first meetings with Steve, I drew a turnstile on the board and he made a face and told me to draw an arrow instead. So I did. So this is what's going to be happening in tonight's talk. So we have types and terms, and then we have, of course, dependent types and terms. So again, these are index that can be thought of as index sets and sections. And then we have equality judgments. And for this part of the talk, what is crucial is that equal types and terms are treated as identical. So it's really the thing we know from mathematics, that we can treat equal objects as identical because they are in this particular semantics. And that was intended as a foundation for constructive mathematics. And to what extent it succeeded, I'm not going to get into that. But yeah, so I personally really like this system. You can do a lot of it, a lot of stuff in it. But homotopy type theory gives a new spin to the intentional version of it, as we will see later. So given extensional type theory, which again is very good to reason about on paper, but not so useful for current proof assistance due to the undecidability of type checking. So the traditional set interpretation is very simple. So types are sets, terms are elements, type of a term of a certain type is just an element in that type. And when it comes to interpreting proofs of identity, these are just elements of a singleton set if the things are equal, or that's an empty set if the two terms are not equal. And this propagates all throughout the hierarchy of paths. So basically nothing interesting from a homotopical perspective is happening there. But again, it's very simple and we understand it. And then how do well-founded trees look like in this system? Well, so the whole idea is that these are structures freely generated by some collection of constructors that we specify. And what does it mean? Well, it should mean that everything that is in the type is really is generated by successive applications of these operators. And so what exactly is a W type? Well, it can be thought of as a type of trees that have finite depth, but possibly infinite or arbitrary branching factors. So it's given by a type A, that is the type of constructors or labels. Let's see some examples. So for example, for natural numbers, we have two constructors, obviously zero and successor. So the type A would be the type of Booleans. For lists, for example, we have of type C, we have 1 plus C constructors because we have the constructor nil. So that stands for the 1. And then we have constructor cons A, cons C for each term C of type C that appends C at the head of the list that we are given. So A is the type of constructors, and then B, which is a dependent type over A. B of A gives the arity of each constructor. So again, for natural numbers, the first constructor has arity 0 because that's a constant 0, and the second constructor has arity 1. because that's a successor that takes one natural number and produces a natural number. And similarly for the case of lists. So what does the soup do? Well, the soup, which stands for supremum, it's intended to basically combine all the branches that are given to us inductively into this one tree that has the constructor A in the node. So that's why soup takes the constructor A, some constructor A. And then for each position, for each argument position, it supplies a tree, like a branch. So it has BA many branches. And then all of these branches are combined and produce a new tree. And this is the only way that we can actually produce a well-founded tree, which means that we get to our principle of induction. So if we want to prove some property PW for each well-founded tree W, then it gives there are two insights. Well, first of all, it suffices to prove it for the canonical forms of such well-founded trees, which are exactly the ones produced by the supremum. And also, we can use the inductive hypothesis that the property holds for each of the branches, for each of the subtrees, because they have strictly smaller depth. So here there is something entirely trivial almost going on in the observation that that in order to prove something for all well-founded trees, it suffices to prove it for the canonical ones. And it's almost trivial because if that's the only way we can produce them, then it makes sense that we only have to prove whatever we want to prove for trees of that form. But as we will see in homotopy type theory, that is actually not quite the case for all inductive types, which is why the principle of path induction, for example, is so interesting, because there we will actually have ways to produce non-canonical elements of an inductive type, but yet the induction principle still holds. So that is something that I still don't quite understand to this day, how that's possible. But yeah, so, okay, but coming back to W types, what does it mean type theoretically, since this is a bit hard to, so the homotopy initiality and initiality in general, as we will see, is super easy to describe categorically, because that is actually a categorical notion. We have some universal arrow and so on, but this is a very syntactic type theory notion that is very hard to translate directly into syntax, into semantics, and then reason about it categorically, which is why we stick to type theory and use it as basically an internal language to reason about categories. So type theoretically, this means that if we're given a function that takes a constructor and together with appropriate arguments, so that's the A and the F parts, the A and the F arguments, and we also we know that for each argument P holds, which is where that's the third argument to E, the inductive hypothesis, then we can conclude that the property holds for that given one-form tree produced by taking the supremum. So this is the recurrence, one could say, that we are operating with. And if we specify that recurrence, then the initiality of the induction principle for well-founded trees gives us a function that more or less basically acts exactly as we expect on the canonical elements, namely the way we specify it should via the recurrence E. So, for example, we have two obvious ways, and this will be captured in one of the proofs that we will see later. We can express the identity map on W directly in the obvious way, or we can do it inductively by using the induction principle of the type of well-founded trees, and these two characterizations coincide. So why exactly are initial algebras as well-founded trees? Exactly the same thing. Well, it's useful to go over the proof. So I don't actually know if this proof was ever written somewhere. I think many people reinvented it at some point. It was basically a folklore result, but it is, I think, originally due to Peter de Beer, though I can't remember if he wrote it out in detail. Maybe it was too big to fit in the margin. So given an initial algebra for a polynomial endofunctor that corresponds to the data we have, the A and B, now we know that the algebra now consists of the carrier type, which is the W, and the arrow, which is the sup constructor. So it goes from the sigma type that packages up the A and the constructor together with its arguments, and then produces something of type X. Right, so if we have an algebra like this, then so we do already know that we have the sup constructor, and it remains to prove the induction principle. But of course, this is where bulk of the work lies. So to this end, let P and E be given. So in order to use the initiality of W, we must somehow produce an algebra, because what we have, P, can be seen as some form of an indexed algebra, but P is not itself a type. So we do the obvious thing, and we consider the total space of P. So it's a sigma type together with the base W that P is fibered over. So that this way we have a carrier set. And well, this is just to remind us what the endofunctor is. But now, in order to actually use initiality, we need to endow this carrier set with the algebra arrow, with the algebra structure. And so to this end, what are we actually doing? Well, we need to go from the sigma type up there down to the sigma type, the total space of P. So what does that mean? Okay, so this seems like a very complicated expression, but actually it's really the only thing we can do. So let's parse it together. So we need to land in the sigma type in the total space, which means that we need to have a product, so a pair of things. And so the first thing needs to land in W. So the only way we can create a well-founded tree is obviously by using the sup constructor. So we need to supply a constructor or a label. So the only thing we have is the A. And now we need to give A its arguments, which is a collection of things in W. So we take the argument position B, and now what do we do with it? Well, the only thing we can do with it is we have this F sigma up there, which, however, doesn't land directly in W. It lands in the total space of P over W. So F sigma of B gives us a pair, the first component of which is in W, and the second component of which proves that the first component actually satisfies P. So we construct, we destruct this, and we take the first component, and then we have something in W. So then we can form the sup at the supremum, and that becomes our first component of the pair that we want. And now, since we are constructing something in the total space of P, we now need to prove that P of that actually holds. And when I say holds, I mean it has an inhabitant. And we know how to construct inhabitants of P of a supremum because that's where the recurrence came from. We have the recurrence E. Okay, so what do we do with it? Well, the first two arguments are obvious. Those coincide with the first two arguments for the soup. And the last argument needs to prove that each of the arguments, each of the branches passed on to the soup actually satisfy P themselves. But we know this already because the F sigma up there actually pairs up each branch with the proof that P holds for that branch. So we just extract the second component instead of the first one. So this means after all this work, we have an algebra, and the initiality of W now gives us a map into this algebra. So now we are almost done because what we really wanted was something that lies in P. It's basically a section, and we can construct a section by simply taking out the second component of F sigma applied to W. But of course, there is a little caveat. We must show that, well, strictly speaking, all we know at this point is that F sigma of W lies over, or the second component of F sigma W is in the fiber over the first component of F sigma W, but we really want it to be over W. But fortunately, we defined our algebra in such a way that the first component is really just W. And why can we prove this? Well, that's where the uniqueness part of initiality comes from. So we have two maps, and we want to show that they're equal, and they're out of an initial algebra. So what do? Well, we prove that they're actually algebra morphisms, and then it will automatically follow that they must be equal. So this is pretty clear, I hope. Okay, so then the only thing we need to show really is that pi1 composed with F sigma is an algebra morphism. Well, and this follows just from the fact that F was constructed, if we remember, F sigma was constructed by induction. So F sigma is actually an algebra morphism itself. So using that and applying the first projection to it gives us that the composition of the first projection and F sigma is itself an algebra morphism. So then we're done. So that's the very basic structure of the proof in the extensional case, or at least the direction that allows us to deduce the satisfaction of the induction principle from homotopy initiality. The other direction is even easier. So we're not gonna go into that because this is where all the interesting stuff happens. So now, when we come to homotopy type theory, how did things start? Well, as I said, with Audi and Warren and Voivodsky, who came up with several interpretations of intentional type theory, where they observed that, earlier we had this type theoretic description of equality judgments, and there it was maybe not so interesting to reason about when two sets are equal. From a categorical perspective, it's obviously more interesting to reason about arrows, but actually these people showed that if we replace the equality sign in our mind with these things are not identical, but there's an equivalence between these two sets, that means they're isomorphic in some sense, then that becomes very interesting, because obviously we all care about two sets or two structures being isomorphic. And they showed that essentially all of the properties that we expect from the type, when we work inside the type theory itself, work just as well when we interpret this equality sign between either between types or between terms as a type of paths, so in a proof relevant way. So things aren't just equal or not equal, but they can be equal, related, in very many ways that can again be themselves related in many ways, and so on. So there's this infinite hierarchy on each type, basically. So if we go back to where we were, okay, and so why is that something we care about? Well, as I mentioned, formalization is a big part of why we, for example, care about homotopy type theory, because the step from real mathematics to a formalized proof is currently very, very large, but the step from a proof expressed in homotopy type theory to a formalized proof is not so large anymore. And in fact, the type theoretic reasoning can often very much simplify existing proofs of known results, to the point that maybe even, well, this is perhaps the first fundamental result that we had, but since then, since Likata-Schumann 2012, we had very, very many results in synthetic homotopy type theory, formalized in various proof assistants that showed some very novel insights, and in fact shortened many of the classical proofs. And the geometric intuition that comes from Voevodsky and abstract homotopy theories and higher category theories can be used to motivate further type theory constructs and further systems, actually. Now we have cubical type theory, various versions of it, that is motivated almost entirely by geometric intuitions, and a lot of things can be done in it, maybe even better than, well, not maybe, definitely even better than in the book Homotopy type theory that we have here. So if we remember the old set interpretation, we forget about that one, and now we have new interpretation, where now types are topological spaces, so not just sets, but sets with a structure. Terms are again points, but now paths P from A to B are actually paths from A to B in this topological space. And paths from P to Q, where P to Q are themselves paths from A to B, are homotopies from P to Q in A, so continuous transformations from P to Q. So we can picture something like this, where we can go from M to N, and then perhaps there is some disconnect. So we cannot really go from Q to M because Q lies in a different connected component. And what can we do with these paths? Well, they behave, type theoretically, they behave almost exactly as an equality would. So we have reflexivity, symmetry, transitivity, so we can compose things. They're functorial, so we can do all sorts of nice stuff with it. So, as I said, the very first project that I had in homotopy type theory many years ago was explore what inductive types look like in homotopy type theory, and whether we can save the correspondence that exists in extensional type theory but doesn't exist in the intensional version that homotopy type theory is based on. So what can we say actually about algebra, about initial algebras versus inductive types in homotopy type theory? Well, let's consider a very simple end effector for the natural numbers. So obviously we know what an algebra is for this functor, right? But now we remember that we work in a proof relevance setting where things can be equal in multiple ways. So a morphism is now not just a function that satisfies some commutative diagram period, but it's a triple where we have a function f as before, but now we have two witnesses that the respective two commutative diagrams actually commute. And this is important because we may have in principle very many witnesses or none, in which case it's not an algebra morphism. But if we have very many witnesses, then depending on which witnesses we choose from, we may get a different, well, we may or may not get a different morphism. So now we have type of morphisms as the type of these triples, and an algebra is a homotopy initial if we consider the type of morphisms from that algebra to any other algebra. It is contractible, which means that it has a unique inhabitant up to equality. So it may have, so we know that there is such a morphism. And then moreover, any other such morphism, which again is not just the function, but the function together with the witnesses of commutativity, then any such triple must be equal to any other triple that we have out of the algebra X. So this is basically a very simple definition, but it's enough to restore the correspondence between almost any inductive type we can think of and the homotopy initial algebra for the appropriate endofunctor that defines that type. So for example, indeed, natural numbers with 0 and successor are homotopy initial. That structure is homotopy initial among algebras of the requisite form. So let's see how to reconstruct this argument. So to prove the induction principle, again, we have P and E. And this is, again, the same thing as we had before. So this part of the argument doesn't really change. And again, this seems very simple so far. We endow the algebra with exactly the carrier set with exactly the same algebra structure as we had before. And now, again, very simple. Instead of initiality, we say homotopy initiality gives us the function that we define by out of W. But now we recall that the key reason why we were able to actually define our desired map F was that the first projection composed with F sigma was actually the identity on the nose. This is now not the case because we are in an intentional setting where equal things are not interchangeable, strictly speaking. They are interchangeable from some meta perspective in the sense that whatever holds for one thing holds for the equal thing, but some work is required sometimes in transporting the structure. So here, as we will see, we will be able to show that the first projection composed with F sigma is indeed the identity, but we cannot simply just pretend that these things are now totally the same. We actually have to transport, so to speak, using that path alpha W. We have to transport the second projection of F sigma W from the fiber that it lies over, which is over the first projection, to the fiber we want it to lie over, namely the fiber over W. But so far, it still seems pretty simple, except now we have to actually construct alpha. And what do we do there? Well, again, this is clearly going to be an algebra morphism. And here we proceed to prove that the first projection composed with F sigma is an algebra morphism. We do exactly the same thing, except now we have to keep track of the names we give to these equalities. So the first path now follows from the computation rule, and we have to remember that this is not just some arbitrary equality that we treat opaquely, but it's really this one that comes from the computation rule, and the second one is just these things are identical, so that's going to be just the identity path, reflexivity. Well, the above two paths are indeed equal, but we're not done yet, because in the rest of the proof, so because we remember actually that our induction principle wasn't just the function that we wanted, but it also had to have this particular computational behavior, because when we construct things by recursion, we actually wanted to satisfy the recurrence that we give it. And to actually be able to compute with such a function, it is crucial that this alpha, which is called the homotopy because it's a family of paths, the alpha that is induced by the equality of the two morphisms now must be coherent. And that's the interesting / very annoying part of HOT, is that every time you have a path, as long as there is another level to worry about, you have to prove some coherence. You have to prove what the path actually does or how it's constructed. You have to know something about it. And in this case, what we need to know is that the path acts exactly as expected on canonical elements, in this case, on canonical well-founded trees. So in particular, it means it itself must be defined by some form of recurrence. And the recurrence is now a commutative diagram. So on the left-hand side, we have this is basically this equivalent, this series of equalities that we have up here. On the right-hand side, the right edge is just the identity. And now up there, we have alpha on the canonical element soup. And down there, we have alpha on each of the branches. And they're put together via function extensionality. So here we see that, in fact, function extensionality is a very necessary component to even go one way, to even be able to deduce the induction principle from the initiality part. And it's, of course, also necessary in the other way, when we want to show that the inductive type is indeed initial, we have to be able to reason about the equality of the morphisms, which are functions. So once we know this, then we are able to actually carry out the proof that indeed the thing we constructed on the previous slide, on the previous slide, here the FW is going to have the requisite computational behavior that we wanted, that we want it to have. So from this, somebody can be very nitpicky here. I don't expect people to be, but it's possible that they could observe that here, what we really have, so we prove that this function we constructed has some form of computational behavior, but we prove it by proving it. So it's not going to be definitional on the nose. And the very interesting part about this is that, so this is captured with the parenthesized remark that these inductive types have propositional computation rules. So they are, in a sense, more general. We don't impose that they satisfy certain computational behavior on the nose, but only up to the requisite equivalence. And the interesting point is that it is still not known to this day whether a theory like this with propositional computation rules is in any way weaker than the theory where these computation rules, or some of them, are actually definitional, at least not in the presence of univalence. So in fact, the cubical type theory, or a version of cubical type theory, has many more definitional equalities, many more things compute than in homotopy type theory, but we still don't know if these versions of cubical type theories are in fact conservative over the book homotopy type theory. So for all we know at this point, the definitional form of the definitional computational behavior may just be convenience or not, but I think we all hope it is. So, right, so let's say we prove this. Okay. And so where do we go from here? Well, we already did. I mean, you can try to redo it, but this is in my thesis. Basically, we established the same correspondence for a higher inductive version of W types, which allow us to specify not only how to construct well-founded trees, but also how to impose some equations upon them. So it also allows us to assert constructors for path types, not only for the type that we are inductively defining. And of course, likewise, the homotopy initial algebras of the appropriate form are going to correspond precisely with W quotients, or with the induction principle. But there is a caveat, namely that we now don't really have an obvious non-trivial polynomial functor to associate with these initial algebras. So they're structures of some form, but since we have not just the underlying sets to worry about at this point, but also the path spaces over the underlying sets, I don't think it has been currently worked out what they are algebras for, really, if there is some sort of a higher functor or something like that. And oh yeah, I wanted to mention one more thing, that perhaps you noticed that for the initial algebras, it said initial algebras are well-founded trees and vice versa, but here we have an equality. And why is that? Well, because in the proof-relevant setting, we actually, it could in principle be possible that something can be homotopy initial in more than one way, or an algebra could satisfy the induction principle in more than one way, in ways that are not equal. But actually, part of the result is that this is not possible. That if such an induction principle exists for an algebra, then it is unique. And in that case, the algebra is also homotopy initial and vice versa. And the structure of homotopy initiality on a given algebra is also unique if it exists. So this is called mere properties. Mere in the sense that they don't actually carry any computational content themselves. So, and the W quotients turn out to be an interesting class that perhaps corresponds to, in a higher sense, fulfills the same role as W types fulfill on the zero level, that of some reasonably simple class of higher inductive types in this sense, that subsumes maybe many or all, perhaps even, instances of higher inductive types that we care about. And for any specific higher inductive type, we can inherit the characterization as a homotopy initial algebra without having to redo all this work that we did to establish the characterization for W quotients. And I think now Mike and Peter Lumsden, Mike Schulman and Peter Lumsden have finally completed perhaps their paper on the schema for higher inductive types. So perhaps that is an alternative approach that gives an answer to how to define a higher inductive type. So thank you very much. I think I'm out of time.
Thank you, Kristina. Let's see. People can now unmute themselves. If anyone has any questions.
Oh, hi, Nicole.
Hi. There's a bit of a miracle when we did this work, namely that when you look at the identity types between two algebra homomorphisms and you unfold what that means, it gives you exactly what an Australian category theorist would call a algebra two-cell. So I'm wondering if the same phenomenon arises for other kinds of higher inductive types that you might have looked at.
Absolutely, yes. So actually, that is a crucial, thank you, Nicola, for that observation. That is a crucial step, in fact, in the characterization, because we need to go from the abstract description of having a path between two algebra morphisms to a more concrete one of having, for example, the homotopy and the coherence diagram. So that's what the two-cell actually is, and this is a, I mean, the proof wouldn't really go through without it. But now that reminds me, again, thank you for that remark, that we have a similar, we can also now characterize the path space between initial algebras or between algebras in general as isomorphisms that satisfy, that are algebra morphisms. And also due to univalence, this now follows that any two initial algebras are basically interchangeable in the sense that they satisfy exactly the same type theoretic properties, and it doesn't have to be, so it doesn't have to be hand-waved around as in math. Like, yes, isomorphic things, we all know that isomorphic things are equal, but we actually, this is actually a formal statement now that follows from the induction principle, induction elimination. So yes, thank you, Nicola, again.
Great. We can still see your screen, by the way.
Oh, okay. Maybe I will cancel. Oh, stop sharing. Does it work now?
It looks good.
Okay.
Other questions for Kristina?
Okay.
I have a question.
Hi, Steve.
Please.
Hi, Kristina. I'm going to have to learn to trust you. I always get nervous that you're not going to make it and that you start too slow, and then you always make it. So I'm just going to have to learn to trust your timing. Anyway, thanks for that. Another cool thing about this theory, I think, is when we started out doing it, we were thinking of the usual inductive types and trying to fix the universal property. And then we introduced the homotopy initiality, and then everything worked fine. But then kind of after the fact, what we realized was, hey, we can be making inductive types or W types where the signature is also higher dimensional, right? It doesn't have to be like lists or natural numbers or something like that. We could have a polynomial endofunctor that's got a 1 type or an n type in the base, and then a family of higher types. So, and we still can make initial algebras for these things, and the whole theory still works. I think it was Thorsten maybe, but also somebody earlier who said, well, these things are really analytic functors or some kind of species. If you've got a higher type in the base, then when you write the polynomial, you know, really, it's not just a disjoint sum. It's got some action by the paths in the base in it. And then the W type is going to be some kind of, I don't know what, we'll let the homotopy theorists explain what the W type is for such a higher structure. So just for example, a really simple example would be, let's suppose in the base, instead of having, like for the natural numbers, you have just 2, and then you have whatever, and then you have 1 going down to 2. That's the family that generates the natural numbers as its W type. It's 2 in the base, 1 up on top, and then just 1 goes down into one of the endpoints. That's the family. Instead, let's put in the base, let's put S1, the circle.
Mhm.
In the fiber, we put 2, but then we twist it as we go around. So we got the double cover of the circle. Okay, that's a fibration. Now, what's the polynomial functor of that thing? And what's the W type of that thing? I think that Nicola's student verified Egbert's observation that the W type for that is symmetric trees, binary branching trees with symmetries. Does anybody remember that? Maybe Kristina probably knows.
Yes, but I forgot which student that was, to be honest.
I forgot his name. Nicola knows his name.
Yeah.
Jakob Widmar.
Yeah, that's him. Yeah.
Oh yeah, that's right. That's right.
And but you could do anything. You could do the hop vibration. So we have that hop in hot. What's the W type of the hop vibration?
I don't know. Do you know?
I don't know. There's all kinds of cool stuff you could do. So anyway, I just wanted to throw that out there.
Great, thank you, Steve.
Thank you, Kristina. Good to see you. Kind of.
I just want to jump in before Thorsten in order to embarrass him, because we did a bunch of stuff in the late noughties on observational type theory, in which a whole bunch of things worked, but equality was still proof irrelevant. And this thing about W types was one of the things that worked. So it is not necessary to go as far as homotopy type theory in order to have W types behaving sensibly. On the other hand, it's certainly worth going as far as homotopy type theory, but for much more interesting reasons.
Yeah, so actually Connor is right. So the problem actually went the other way. So I was given a problem to investigate the behavior of inductive types in homotopy type theory, because that was the thing that was going on at that time at CMU with Vladimir and Steve. So of course, yes, you're right that we don't really need to go quite as far. But if you do want to reason about, Hopf vibration, then I'm not sure about, I don't know that the observational type theory suffices for that. So if you want to
absolutely, I'm not claiming that we should have stopped there. And the new stuff is absolutely lovely stuff, but the old stuff got some of the way, and had some quite attractive properties when you're engineering a proof assistant, in terms of definitional proof irrelevance and all of that sort of stuff. So it's lovely to be aware of proof irrelevance when you can have it, as well as acknowledging that there are very useful notions of equality that are not proof irrelevant.
Definitely, yeah.
Let's have it both ways.
We can.
Can I also?
We have time for a very quick question, but
no, I want to. A very quick remark, which is related to what just was discussed. So I gave some examples for interesting higher containers, namely, for example, so S can be the groupoid of symmetric groups, and I also give the functor into set, which is the obvious one. So this way, you get a version of multisets, but they're not really the multisets you want, because they are a one type and you wanted to have a set. So you're one level up. Now the problem is that truncation is not a container, not even in the generalized sense. Yeah. So you have to move. You have to move beyond groupoids to get truncation. And here is a possible solution. If you replace, if you go to directed types theory, replace groupoids by categories, then it turns out that truncation is a container, is a category container. And this way, you get all these interesting containers, because you can just compose the thing I just described with truncation, and you get a category container. Sorry.
Great, thanks for all the questions, everyone. Sorry to kind of cut things off there, but thanks, Kristina, again for your great talk. And
thank you for inviting me.
Certainly. And next we have Michael Batanin. Are you there, Michael?
Yeah, I'm here. Greetings from rainy Barcelona for everyone. It's unexpectedly rainy.
Great. You want to try sharing screen?
Yeah. Should I just share? I'm not sure what the result will be. But, okay, let's see. So. Hop. I don't know.
Looks good.
Now you can see.
Yes. So we're very pleased to have Michael Batanin talking to us about Grothendieck homotopy theory and polynomial monads. Go ahead, Michael.
Thank you very much, David, and thank you, organizer, for this opportunity to speak in such a nice meeting. And what I'm going to speak today is two subjects together: Grothendieck homotopy theory and how polynomial monads can be useful in such classical subject already. But in fact, this time is short. For some reason I cannot move. Okay, now it's moving. Yeah, and so I will introduce Grothendieck homotopy theory just step by step, as much as is needed. Mostly I will speak about different construction, which what I call Grothendieck homotopy theory toolbox. And the goal is to extend this construction from category of small categories, where the main place where the homotopy, the Grothendieck homotopy theory takes place, to the bigger category of polynomial, actually finitary polynomial monads in sets. And because everybody here knows what this means, we know that cat sits inside that polynomial monads in set as a full subcategory, so it should be considered as a real extension. And what is Grothendieck homotopy theory toolbox? Of course, I cannot just describe everything in this theory. It's quite big. But main ingredients, I would say, is Grothendieck constructions and slice categories, and some fundamental theorems like Quillian theorem A and Thomason theorem, and the theory of spherical or cofinal functors, and also exact squares and smooth and proper functors. But I don't think I have time to mention much of it, but it can be done. And final subject is locally constant preshifts and Ciesinski localizations, which I'm going to again extend to algebra of polynomial monads. So the first thing I want to remind you, as I said, a fundamental thing in all these theories, Grothendieck construction, and in fact it's left adjoint. And what is Grothendieck construction? Of course, again, everybody knows, I'm sure, but it starts from a small category and a functor from a small category to category of categories. And then we can construct another category whose objects are pairs of A and X, where X is an object of a value of F on A. And morphism and some other pairs, again, F, which is morphism between objects in A, and phi is, of course, a morphism now in the values of this function, of this functor F. So, of course, we have a projection from Grothendieck construction F to A, and this projection has very nice properties, as fibrations, etc., but it's not important at the moment. What is important is that we can consider this as a functor from preshift category with value in cat on A to the slice category of cat over A. And indeed, this is even two functor. And this two functor has a two left two adjoint. And this is again very familiar constructions called slicing, or just construction of a homotopy fiber of a functor. So what we do, we take a functor from B to A, which live, of course, in this category, and we associate a preshift on category A, just given by slices of this functor U over each object A. Of course, it's a classical what the slice category means. Of course, that's why just morphisms are arbitrary arrows in category A from UX to A, and objects are like this, and morphisms are triangles of this form. So this is very well known. So but the most important thing to remember that this left to adjoint. So in the rest of the talk, what I will show that there is similar construction for polynomial monads, and we also have left adjoint with all consequences which we can extract from this. And of course, first thing I want to describe is the existence of Grothendieck construction for polynomial monads. Now I start from a finitary polynomial monad, which is some sort of bridge, which in my writing is collapsed to a line, but some people say that it's a bridge. And so, but now what the second ingredient for Grothendieck construction, it's not a presheaf, it's algebra of such a polynomial monad with value in cat. Of course, since it's just a functor, it's a polynomial monad, so it might have some algebra in any symmetric monoidal category, in particular in cat. So I just take cat value algebra, and then I can construct another polynomial monad, which we also call polynomial Grothendieck construction, which is very much similar to what we just saw for classical Grothendieck construction. Again, objects of this new polynomial monad, or colors, if you want, are pairs, which I is a color from I, but A lives in the value of f of I, because what is algebra? First of all, it's a family of categories, fi, and so I can take an object of fi. But now I also have to say what is operation on this polynomial monad. What I call operation is this space B here. And operation, of course, is given by some operation with a lot of decorations now. So I have to specify, but probably not so important. We just have to think about this as a multimorphism, and we can decorate it appropriately and get another multimorphism and get a morphism, which indeed now is multimorphism, where M is multiplication in the polynomial or compositional law in polynomial monad T. And so it's very similar construction, but just multi-sorted construction or multi-variable construction compared to the usual one. So again, this Grothendieck construction comes with Cartesian morphism of polynomial monad from Grothendieck construction to T. So why it's important? Because this also can be considered as a factor from algebra in the value of cut of T to polynomial monad over T. And this is even two factor, and it has a left adjoint. So of course, what I want to construct now is this left adjoint and explain what this left adjoint means, because it's quite remarkable. It has a different aspects which normally people don't look at the slice construction. So this is analog of slice construction for polynomial monad, but can be understood from different angles. So the simplest example is out of a category of small categories. If you take, say, a free monoid monad, of course, everybody knows how to describe it as a polynomial. It's a polynomial monad. And what are algebra of this monad? Of course, they are strict monoidal category. So let's take one of these M. And then I want to construct a Grothendieck construction. And this will be a polynomial monad which has the same object as F, but which operations or multimorphism as just F, which is strict monoidal category. It's a home in this strict monoidal category from multiple tensor product of A1, AN to A. And this, of course, sounds very familiar to people who work with operators in the monoidal categories. It's a standard construction of non-symmetric operator out of a monoidal category. And what is left adjoint for this? Again, this is very well known. If we have polynomial monad over M, where M is monoid, this free monoid monad, then such a polynomial monad is just non-symmetric operator. So we allow, of course, colors or object be arbitrary. So this is just colored non-symmetric operator. And then we can associate a strict monoidal category of it by classical again. So this is a very simple instance of this junction. But we are going to go further with this. So now I want to say more about this construction of left adjoint, because it's in some sense it's the main players in all the theory. So we have this special name for this. We have this left adjoint, which we call T to the S, and we call classifier of internal S algebra inside the categorical T algebra. So it's a bit long name, but why such a name? It's just because we can describe it really like something internal, some kind of internal structure, which classifies some internal structure inside categorical algebra. So if we have a Cartesian morphism between monad, so of course we have a restriction factor from algebra T to algebra S, and this is two factor, and we call a categorical algebra actually this should be S algebra. Yeah, so it has to be a categorical S algebra inside a categorical T algebra A. Yeah, so I think it's correct. So S algebra. It's just a lax morphism of S algebra like this. So you take the terminal algebra, one here it's terminal algebra of S, and we just take lax morphism to restriction of A to phi star of A, which is a restriction factor. So very simple example why it makes sense to call internal algebra. Say start from identity factor from M to M, where M is free monoid monad. So what we obtain Of course, an internal algebra is the same as a lax monoidal functor from 1 to A. And of course, again, it's a classical observation, which goes back maybe to Benabou, maybe earlier, I don't know exactly who was first, which this is just the same as monoid in A. So monoids are internal algebra inside such M with respect to this identity functor. So this is, and another point of view of this internal algebra classifier is that in fact this is some representing object of some natural two functor, and this two functor is just the following: take categorical algebra of T and consider all internal S algebra inside categorical algebra of T. This will be a functor to ket, and this classifier is just representing object for this. So of course I have this proof here, but I am afraid that I probably will skip the proof, and if you later have some question, I can come back to this and explain. But another important aspect of this classifier, and why actually they are useful, because there is a representation of this classifier's functor in terms of codescent object, and this makes it very much appropriate for calculations, because that's actually how we compute classifiers. So it's in very simple case again, if we have, say, identity morphism from T to T, it turns out that the classifier is just descent of such a simple truncated codescent object of such a simple truncated simplicial object, which is of course a bar construction of terminal T algebra. It's exactly the same. It's just bar construction. And codescent in this case again means something very simple, because everything is discrete here, and in fact this object satisfies single conditions because of Cartesianness of T, and so we just have an internal category in the category of T algebra, and this is exactly the codescent object. So we can compute it very explicitly as a result, because we know everything now. And the more general classifier, of course, is also codescent objects, but not of this simple bar construction, but slightly more complicated two-sided bar construction. But in principle, it's kind of the same. Instead of one, we have application of this left adjoint to one, and we continue with the same bar complex. So it's highly computable. And now examples of classifiers. And of course, as I said before, that in case of small categories, if you're given just a small functor between small categories, which is the same as linear polynomial monads map, and algebra of these are just presheaves in ket, and then the classifier of T to S will be just this presheaf of slice categories, which I mentioned. So it must be a presheaf over T of categories, so that's what it is. Okay, what about free monoid monad? Again, it's something very familiar, because M algebra again is strict monoidal category, and the category of internal algebra is category of monoids, and we have to classify monoids inside strict monoidal categories, and this is classical result, classical observation of Lavier probably again, that that monoids in A is the same as strict monoidal functor from the category of delta plus, which is category of all finite ordinals and order preserving maps to A. And so this classifier is M to the M is indeed delta plus. There are slightly more interesting classifier, again, not too complicated, but more interesting maybe, because if we can take identity monad, but not identity, but the monad for pointed sets, which is now, again, we are away from linear monad from categories now, because it's just add a point to a set. And what is classifier of this? And it's not difficult to see that it's just classifier of identity map. Of course, it's just an arrow category from 0 to 1, where 1 is a pointed object in this category. This must be pointed category. And we have a canonical morphism from such a simple monad to M. And so we can speak about classifier of M over this monad, over this morphism. And the classifier, it's not, of course, it's not, again, difficult to see that it's just a subcategory of delta plus of injective maps. It's again a monoidal category, but only injective maps. And now we move for more complicated object. If you take, say, now symmetric, say, polynomial monad for non-symmetric operads, and then ask about classifier, then again we get something very familiar for people who are doing operads. We get a category of planar rooted trees with n leaves. So this, in fact, this is non-symmetric operad in cat, which in degree n has this category of planar rooted trees with n leaves. And morphism are contractions and some introduction of new vertex of valence too. And of course, they classify in operads inside categorical non-symmetric operads. So that's interesting thing. And similar for symmetric operads, the only thing we have to change here is that we use all rooted trees instead of planar trees, and we can again something very classical, the category of rooted trees and contractions, which is classifiers. So in fact, this is the main reason how people do operad theory. They very often consider any operad as a functor on some category of trees. And this precisely the universal property of such classifiers. Any operad is a functor of on such category of rooted trees. So this is known from Kapranov and Ginsburg and Kapranov probably, but they don't describe it as a universal property, but this is what it is. Okay, and the last thing about classifier which I have to mention is classifiers from homotopy point of view, because again this will be important. So what we can consider out of monad T, we can consider this algebra now in simplicial sets, and this has projective model structure. We can just lift it or transfer it from just family or collection of simplicial sets over I, and this has nice model structure, so we can speak about homotopy theory. And this is a theorem, how we can understand classifier from homotopical point of view. First of all, I want to understand this, what we call absolute classifier, or classifier of identity map of S, and this is, in fact, we have to take a nerve of it. So take a nerve, of course, I take it just pointwise. So we have, in fact, a family of categories we can take pointwise nerve. And it happens that this nerve is actually confinement replacement of terminal S algebra of 1. So it's exactly confinement replacement. And second fact about this, which is important, that if you want to understand now a general classifier, this in fact can be proved that this nerve of this general classifier is a value of left-right functor of this left adjoint to restriction functor, because phi shrik here is a left adjoint to restriction functor, and this Quillian functor, left Quillian, so we can take left the right functor, and this will be exactly this nerve of a classifier. So this is all about classifiers, and now we can come to this theorem from the toolbox of Grothendieck homotopy theory. And the most fundamental thing for Grothendieck homotopy theory is Quillen theorem A. Let's see how it looks like in polynomial settings. Of course, I have to recall first what Quillen theorem A means. A classical one, maybe a little bit less classical than in less classical form, but it's equivalent. So I recall that a Thomason equivalent between small categories is a factor which induces weak equivalence between nerves of categories. And Quillen theorem A says the following, that given a triangle commutative triangle in category of small categories, such that fiber-wise is a Thomason equivalent. So in each for each object R from here, we have a map between slices of H and G, and if this is weak equivalence or Thomason equivalence, then F itself is a Thomason equivalence. So it's very well-known theorem from fiber-wise equivalence to full equivalence. But now let's see what happened in polynomial monads. And here it takes a little bit different form because we need to go from commutative triangle to commutative tetrahedron. So now we are given a commutative tetrahedron of polynomial monads and Cartesian morphism, of course, between polynomial monads. And then we suppose that, of course, this triangle here induce, because it's a functor, we induce a map between classifiers, and we suppose that it's pointwise Thomason equivalence, like in Quillen theorem A. Then we deduce from here, so the statement is that if we take a map induced by this composite H phi and G phi, we have something induced by this, and this again a Thomason equivalence. So classical theorem can be deduced from this if we put P equal 1, so the terminal category. But in this case, everything collapses actually to the morphism of category, because if this is Cartesian morphism between 2 to 1, then it forces R to be a category, so linear monad, not a polynomial monad. And so this is still just a classical theorem. But in general, it's like this. Okay, so what else? Okay, next theorem, which I mentioned already, is Thomason theorem. But amazing thing here is that in polynomial settings, we have two Thomason theorem, which can be called Thomason theorem. This is the first one, is classical. But first, I again recall classical Thomason theorem. So what it says that if you're given a presheaf of categories on the small categories A, and you take Grothendieck construction and compute its nerve, then it will be weakly equivalent to homotopical limit of nerve of a presheaf of simplicial set of which is nerve of each values f of A. So you take nerve for each A, you take the new presheaf in simplicial set, compute homotopical limits, and this thing is just weakly equivalent to nerve of Grothendieck construction. In polynomial settings, it will be a little bit slightly different, but again, admit very short description. So now suppose we are given categorical algebra. Of course, instead of presheaf as usual, we have to take categorical algebra of A. And suppose we are given a polynomial monad map from A to B. So what we can take then, we can take a composite. Here it's a projection from Grothendieck construction to A, and then we compose it to with phi from A to B. And because of this, we can take classifier of B over this Grothendieck contraction of F and take its nerve. And then the statement is that is weakly equivalent to, again, this left-derived functor of phi of a local nerve. So you can take nerve of F, of course, it will be simplicial algebra, and take left-derived functor, and it will be equivalent. So this is kind of left formula for left Kahn extension rather than for homotopy left Kahn extension rather than for homotopy limit, but not even Kahn extension, but in Kahn extension of algebra. So it's the same formula. And then I come to another Grothendieck construction, which actually will play a lot of roles in applications, very useful also as the first one. But we call it different. We call it twisted Bormann-Fock tensor product for reason which I explain now. Again, what we can start from, instead of categorical algebra of A, we can suppose we are given a presheaf of polynomial monads, like in classical case of Grothendieck construction. And then we can construct a new polynomial monad, which we call again like Grothendieck construction, but with this circle here, because to distinguish between these two constructions. This, in fact, the Lax limit of F in the two category of polynomial monads, and it can be described very explicitly. And to understand what actually is better maybe to look at a couple of examples, which special cases. If F takes value in ket, not in polynomial monad, but in ket, then, of course, if you do this, we just again come down to the classical Grothendieck construction. This is the case. That's why we call also second Grothendieck construction. But now suppose F is a constant functor, which takes for each value A, for each object A, we take value D, a polynomial monad. And then this Grothendieck construction will be just a Bormann-Fock tensor product of A and D. So we consider here A as a symmetric operator with only unary operation, and D is a polynomial monad. Of course, it's a symmetric operator, it's sigma-free symmetric operator. You can take Bormann-Fock tensor product, and this is exactly the value of this Grothendieck construction. So that's why we call this twisted Bormann-Fock tensor product. It's like Bormann-Fock tensor product with non-constant coefficients. And this is second Thomason theorem here. So if we have a presheaf of polynomial monad, but now we consider, suppose we have a presheaf of polynomial monad over another polynomial monad D. If we have such a thing, of course, we have an arrow or map, Cartesian map from F of A to D for each A, and we can take the corresponding classifier. But we also have a morphism of polynomial monad from Lax limit of F to D. So we also can take corresponding classifier. And Thomason theorem says that if you now consider nerve of this D over classifiers F of this second of this twisted Bormann-Fock product, then it will be the same as weakly, of course, as a homotopy limit of nerve of this local classifier dA over D. And this is very useful theorem, which we apply a lot on the application. And in here, I have to come to another instrument of homotopy theory, of Grothendieck homotopy theory, which is called a spherical morphism of polynomial monads, or another name for this are cofinal functors, homotopical cofinal functors. That's how they call it in small categories, but this is now polynomial version. Again, we call a Cartesian map between polynomial monads at W infinity as spherical. It's a little bit long name, and I will explain at the end why I put this W infinity as spherical, because this is one variable which can be used later. But anyway, so it's W are spherical if T is S is W infinity are spherical, which just means that T to S is pointwise Thomason equivalence. Basically means that this classifier is contractible. So this is pointwise contractible. So this is T algebra, categorical T algebra, and we can ask if this is pointwise contractible. So of course, analog for this for functor is just to say that if you have a functor between small categories, then you consider slice categories, and each slice is contractible categories. And then we have a theorem which is very familiar from the theory of cofinal functor, that if a given polynomial monads map with S to T, then it is W infinity spherical if and only if it's induced weak equivalence between derived mapping space from 1 to F to restriction of X for any T algebra X. In the category of algebra of S, there's a mapping space from 1 to X in the category of algebra of T, where 1 is usually terminal algebra. So that's how it allows to compute actually some mapping spaces. Again, these examples, which are first examples, as I already mentioned, that if you consider this, restrict this thing to small categories, then W infinity spherical is the left, what's called by Hitchcock left homotopical cofinal functor. Of course, there are other names for this, but Hitchcock left homotopical cofinal. And this theorem above is generalization of this of the theorem, which states that the functor is left homotopically cofinal if and only if restriction along it preserve the homotopy limits. Of course, it's also analog of classical theorem about cofinal functors, which preserve restriction of them preserve just ordinary limits. But it also can be written in this language. Okay, so more complicated examples actually will be important in later in application of the looping of space of long nodes. So consider the following monad this is polynomial monads such that algebra of these monads are non-symmetric operator together with two different a priori different maps from associativity non-symmetric operator to X, what we call double pointed monad or double multiplicative monad. And consider also by the monad whose algebra are bimodules over us, of course, because us is a non-symmetric operator, it has bimodules, so the left and right modules and bimodules. And we consider bimodules with one additional structure. We want this to be point in degree 1. We have some special point in degree 1. And then we have the following. We have this, there is a natural map between this monad from bimod to n of double star, and this actually W infinity spherical. So what this map is, in fact, it's better to understand this map in terms of algebra, because the algebra of these are non-symmetric operator together with two maps from associativity monad. And of course, we can consider, we use this map R and L to construct right and left action of us on X itself. So in this case, we get a bimodal, but it's also pointed, of course, because we have unit of an operator. So this is how this works, this restriction factor. And it happened to be the W spherical, and the meaning of this I will tell later, maybe when I come to the looping of mapping space. because there is very nice infinity categorical meaning of this statement. That's how we actually guess how to deloop spaces. And there is very similar fact about spherical morphisms between similar bimodals, double pointed bimodals, or double multiplicative bimodals, and what's called infinitesimal bimodals, which also pointed to degree 0. It's also there is this very similar map, which I don't want to go to the details of it. And this will play the role. And final thing which I want to mention is this notion of aspherical diagrams of polynomial monads, which does exist in CAT, but normally people don't formulate it like this. But in polynomial monads, categories polynomial monads is very important to have this definition, because it's one of the central definitions for us. So the first, there is a theorem which says that if given a such again a presheaf of polynomial monad over D, we can construct again this second Grothendieck construction, Ward-Fock tensor product, together with map to D, and then the following conditional equivalence, that this is a W infinity aspherical map of polynomial monad, and for any polynomial monad D for R, a natural map from homotopical limits of nerve of local classifier is the same as nerve of classifier of D from R to D. So this is maybe difficult to understand at the moment, but I'll give you an example, maybe which explains this notion. So again, we call such a diagram W infinity aspherical. So what it means for simplest and the most useful for us is if you have a commutative square of polynomial monads, of course we can consider it as a diagram of the form which I mentioned, because it's you have a category which consists of 3 objects, and this thing is just presheaf in polynomial monads in this category, and this is to get together with this map. So it's a kind of cone. So any commutative square is such a thing, and we call this W infinity aspherical if this is actually W infinity aspherical diagram. And if you translate it, what it says in CAF, the W asphericity here means exactly the following: that if you apply nerve functor for all these A, B, and C, D, this must be a homotopy push-out. This follows from previous theory which I mentioned. So this is equivalent in CAT, but in polynomial monads, you require more complicated formulations, but it's still quite reasonable and nice. Okay, now we want to apply these techniques for the looping of mapping space between point algebra. So what is settings? We start from polynomial monad, and we consider another polynomial monad, which is called P star, and this is monad for pointed P algebra. That is such a monad which is, whose algebra are algebra of P under 1. So it's like multiplicative operas, for example. And of course, there is a map of monad from P to P star. And just forgetful function just forgets this point. And we have restriction functor which forget points, and we have similarly a P double star with again double pointed and monad. And we can write the following push out of monads. This is indeed a push out from P to P star, from P to P star again, and this is for P double star. This is a push out of polynomial monads. And since it's a push out, we have some just identity functor from P star to P star, from here to here, here to here, from P star. Then we have something from P double star to P star, some other natural functor. What it does on terms of algebra, of course, you take a pointed algebra, multiplicative algebra, and it considers as a double pointed algebra just kind of doubles this point. It's the same point, but now we consider it as a double point. So why it's important? Because this theorem, which allow us to compute a loop space of algebra, of mapping space of algebra from 1. So if you suppose that P is polynomial monad, and we suppose that P star and P double star are also polynomial, this is not a trivial condition, because it's not always true that they are polynomial. Then for pointed simplicial P algebra X, and we also have to admit that this square here is W infinity aspherical. And if we have all this condition, then the statement is that the mapping space in double pointed algebra is the same as from 1 to X. If you forget about this, make it double pointed, is the same as loop space from algebra in category of algebra of P from 1 to U star X. So it's allowed to actually replace loop space of in the category of algebra by mapping space in some other category of algebra, and this is very useful observation. And of course, I should mention because there are some conditions to satisfy, and I just list some monads which satisfy these conditions. That of course non-symmetric operat, also left and right modules, bimodules over non-symmetric operats, any bias Dolan plus constructions of any polynomial monads can satisfy these conditions. Also, any left and right bimodules over P plus and etc. etc. So there are quite a lot of monads which satisfy this. So why it's interesting? Because it's allowed to get a new proof of theorem which belong to Dwyer and Hess and Turchin. It's a very spectacular theorem which says that the space of homotopy space, the space of long nodes, so-called space of long nodes, admits a double delooping, very explicit double delooping. This space of long nodes, this n is greater than 3, is equivalent to double deloopings of mapping space of symmetric operator from D1, where D1 is it's a little one disk operator and Dn is a little n disk operator. So it's reduced this complicated space homotopy type of it of double loop space of this mapping space between monad. So this is very important theorem, in fact, and everything actually follows from this. From one fact, of course, from Sinha about this totalization of Kontsevich operator. It was done before, and then we can apply this our theorem for delooping together with these two facts of sphericity of map from bimodules on non-symmetric operator double pointed and bimodules infinitesimal bimodules to double pointed bimodules, and combining these two facts we get this delooping very explicit, and this actually makes it very conceptual, because this proof of Dwyer, Hess, and Turchin, the first proof of this, are very technical and absolutely, at least for me and for many people, as I know too, is very difficult to understand what's going on there. It's just pure techniques and very hard to understand. But this gives a very conceptual explanation, which also allows some generalization, which I don't want to speak about now because it's my time is coming to the end. I just want to mention some other aspect which is important in this Grothendieck homotopy theory, that instead of using W infinity as here, we can use any Grothendieck fundamental localizer W and can make all this theory parameterized by W. What is W fundamental localizers? So it's like class of maps between small categories which satisfy Quillen theorem A and also saturated. And this thing allows to construct some kind of axiomatic theory, localization theory and there are many aspects of this work, so I don't want to touch it now because I have to finish now. What I want to say is only one theory here, which is that this theory of polynomial monads also allows to construct a theory of W locally constant algebra. So this algebra such that it's of polynomial monad such that if you restrict it to unary part, it will be W locally constant pre-sheaf. And this is very interesting aspect of this work, because I just want to mention one. There are several theorems which unfortunately I have to stop here, almost stop that. If you do this for n operads and symmetric operads, you get some stabilization theory for symmetric operads or for n operads, which in fact generalize bias-Dolan stabilization hypothesis for higher categories and classical Freudenthal stabilization theory. But don't have time to speak about. But what I want to mention, the last thing, absolutely last thing, that we all know that finitary polynomial monads in sets are the same thing as sigma-free operads in sets, but we want, of course, to extend this theory to a bigger category of all operads, maybe. So how we can do this? Okay, there is a way to do this. We should use Mark-Weber approach to operads, and with this approach in operads, it's maps of Cartesian map of polynomial monad from P to category of symmetric monoidal categories. And then there is a corresponding Grothendieck construction, also classifier theory. And then we can basically repeat everything for what I call here, which is a little bit of complication, because into classifier will be harder to compute, because it's really now proper codescent, but still computable. And classifier here over SM, it also has interesting meaning, because they are exactly Feynman categories in the sense of Kaufman and Ward. And all Feynman categories are, in fact, are classifiers, nothing else. And even more interesting and exciting for me would be to generalize it to the analytic monads developed by David Gepner, Joachim Koch, and Hausen. And it seems like all theory in these settings will go even smoother, but it's things for future and maybe for somebody else. So thank you very much for your attention, and I have to finish here.
Thank you, Michael. Okay, so people can unmute themselves and ask questions.
That's a beautiful talk.
Thank you.
I just feel speechless. I will need to really read very carefully your slide in order to be able to ask a question, but I'm very interested.
No, thank you very much.
Just
yeah.
a comment.
I'm happy to explain if you just ask me.
Okay.
Okay, well, we have a raised hand by Brendan Shapiro, I think might have been next.
Also, thank you. I really enjoyed this talk. I'm wondering, as you're generalizing the Grothendieck homotopy theory from small categories, if you might have or think there could be some notion similar to test categories of characterizing when these algebras have a model structure which is equivalent to spaces or some other familiar model structure.
So, well, your question is about which, in fact, we can do this, and there's something which I missed a little bit here, because I was talking about this locally constant algebra, And if your category in question is underlying category of question is one of these test category, then you can of course get algebra which are equivalent to the algebra, say, on how to say, just to say for simplicial sets, it's algebra on the usual homotopy types, basically. So yes, you can do this, but this is a little bit outside of possibility to explain right now, because I really have to explain a big chunk of the theory of locally constant algebra for this, but it exists here. So
you would get something like a notion of test polynomial monad?
Wyszynski structure, and you can also generalize this to categories, and it also exists. And it's a lot of stuff can be lifted from Wyszynski book or Marciniotis book, whatever can be lifted to algebra instead of presheet.
Thank you.
Thanks, Brandon. Maybe let's go to Nicola next, even though I actually think Richard may have been next, but that way we can let him eat into his own time if he wants to ask. So, Nicola, do you still have a question?
Just maybe a very naive question. Is there an analog of the Thomason model structure for polynomial monads?
Oh, this is something that I in fact, want to know myself. I asked Ikan Nordic for a similar question, and he also answered he doesn't know, but I don't know too. It's obviously not for in these settings for polynomial monad in sets. For example, in polynomial in monads of sets, there are no even terminal object, so you cannot expect such a naive extension. But if you go to, say, settings of Mark Weber, polynomial monads in cat or symmetric monoidal category monad, then it might be that there is a reasonable Thomason structure, but that's what, yeah, but I don't know myself. I would like to know. This is very interesting.
Thank you.
Okay, and Richard?
Hi, Michael. Thanks for the talk. Very, very nice. So you described two different Grothendieck constructions, one for a pre-sheaf of polynomial monads and one for an algebra for polynomial monad in cat.
Yeah.
So can you combine those two constructions? So you could look at algebras for a polynomial monad in the category of polynomial monads with the Boardman-Vogt tensor product. Does that work?
Yeah, in principle, yes, but if I don't think you get something reasonable if you work if you work in polynomial monad in sets, the Boardman-Vogt tensor product of such thing can, if you just multiply it, of course, you can get something which is not sigma free, and so you're outside of the.
Okay.
But if you work in proper settings, again, in say in Mark Weber settings, yes, that can be done. You can combine together.
And then you get a sort of bigger Grothendieck construction that incorporates those other two.
You get some bigger Grothendieck construction which combine both.
Okay, thanks.
Okay, any other quick questions?
Yeah, building on the question that that Nicola asked, if you think that there might be something like a Thomason model structure on polynomial monads, do you expect that it would be equivalent to any model structures that are more familiar with the way that the Thomason model structure is equivalent to spaces?
Yeah, so Thomason model structure, of course, is clearly equivalent to the just usual Quillen model structure. And here I would say that I would expect something like model structure, say, or if you want, on Feynman categories, and because they're the same as operands, and which perhaps is equivalent to something like infinite, maybe infinity spaces or something, but I don't know, really I don't know. I would expect something to be equivalent to infinity spaces, or maybe also to Cesinsky Nordic infinity operas or something, but this I'm not sure. It's something that I really don't know what to answer. I'm very curious to know. I have no intuition. Thomson model structure is a bit strange thing, I would say.
Okay, well, thanks again, Michael, for the great talk. Next, we have Richard Garner with his last of 3 tutorials. So, Michael, maybe you could stop sharing.
So should I stop?
Yes.
Oh, okay, the question is how to do this. And it's not clear to me straight away. Yeah, so what yeah, maybe.
Great, okay.
Maybe I should just, okay, does it work?
It worked, yep.
Okay, very good.
Okay, so now we have the last of Richard's 3 tutorials. So please, Richard, when you're ready.
All right, thank you, and hello again, everyone. We're on the night shift again in Europe, I see. Whereas I'm just starting my day, so maybe I can inject a bit of early morning energy. So last time I got to the point where I actually managed finally to define the bicategory of polynomials that various other people have been talking about. Okay, so we went through this other way of looking at polynomial functors. Let's go right back up to, oh no, let's go back to the start of last time's talk, which is here. So we finally gave this definition of a polynomial as this sort of bridge diagram and its associated polynomial functor. And then basically we saw how to compose these things, just in terms of these representing diagrams. And then we talked about what are the maps of these polynomials. And motivated by the set case, we define them to be given by a pair of maps, like an F like this and a G like this, where this is a chosen pullback square and all the little parts of the diagram commute. Okay, and that in set case, those are literally the natural transformations between the corresponding polynomial functors. And we said, well, for a general category E, they're not exactly the arbitrary natural transformations, but they are these things, these diagrams here correspond to the indexed natural transformations between these things seen as indexed functors between slices, fibered slices of our base category E. Okay, indexed over E. Okay, and so, I mean, and in particular, if I've got one of these diagrams here representing a morphism, then this is how I obtain a natural transformation. Not all natural transformations, but particular natural transformations that are indexed. So the natural transformation arose via something like this. Okay, and so in this way, we end up with these 2 representations of the same bicategory. So there's the 2 categorical representation, which is I look at the polynomial functors between slices of E. So the objects of those of E, the 1 cells are the polynomial functors between the appropriate slices, and the 2 cells are the indexed transformations between those. And then on the other hand, you can reduce that data and so work with these bridge diagrams. So I have an equivalent, a bioequivalent bicategory whose objects are just those of E, whose 1 cells are these polynomial diagrams and whose 2 cells are those funny maps with an F going one way and a G going the other. Okay, and so I appear not to have said it here, but the point is that these 2 bicategories are indeed bioequivalent. So the intensive and the extensive views are related as nicely as you'd like, which possibly means that it shouldn't be called intensive and extensive, because normally intensive is not the same as extensive. So there you go. That's maybe my My nomenclature was not very good after all. All right, so today we're going to do something different. So this is talk 3. And so I'm going to attempt to explain why the slightly sort of fiddly business about figuring out the 2 cells in this bicategory is actually not very fiddly at all if you look at it in the right way. So, and that's going to involve telling you about the universal property of, I guess, E goes to poly E. Okay, so just for an easy life, I'm going to assume that E is locally Cartesian closed in this section. I mean, I think you can probably do this for non-locally Cartesian closed E, but it's not been done. So there is in the literature on this, it's done for locally Cartesian closed E. So I'm just going to stick to that case. So we'll assume in this section E is locally Cartesian closed, i.e. all maps F are exponentiable, i.e. pi along F exists. Okay? So that's what locally Cartesian closed means, if you didn't already know that. And so I guess to motivate what I'm going to tell you, we're just going to observe that polynomial functors, well, what do they involve? They involve things like sigma left adjoint to delta, left adjoint to pi, satisfying Beck-Chevalley and distributivity axioms. So that was the key to this normalization algorithm. Remember that we had these various 2 cells, which on the face of it were just 2 cells, but turned out to be invertible 2 cells. And the point is that, I mean, what's it all about? It's about certain maps that are adjoint to each other, certain 2 cells that are obtained from canonical coherent 2 cells by transposing under those adjunctions. And that's stuff you can make sense of in any bicategory. So we can make sense of these ideas, kind of adjunctions and coherence data in any bicategory. And so I guess this is just to sort of motivate what I'm about to do now. Motivating the following universal property. So that's probably a slightly vague statement, but hopefully it'll become clear as I start doing it. All right, so I'm not actually going to do poly just yet. I'm going to start with a warm-up by looking at span. Okay, so kind of warm-up. Span. I say span of E. Okay, so if I've got a category with pullbacks E, then there's a perfectly nice category of spans in E, or bicategory of spans in E. And I'm going to explain to you the universal property of this. So this was a result from 2004, and by Thorsten, Perret, and Pronk, and I will tell you about this first. So let's suppose E is a category with pullbacks, in defiance of my assumption that E is locally Cartesian closed. So I guess for this first little bit here, it just needs to be a category with pullbacks. And let's suppose that K is any bicategory. So a delta functor, oh dear, delta functor, F from E op to K is just a pseudo functor with action written as so x goes to fx, and then f from x to y, I'm going to write that as f sub delta of f going from f of y to f of x. Okay, so it's a pseudo functor, so it only preserves composition up to coherent invertible 2-cell, but I'm not going to dwell on that. All right, so why have I called that a delta functor? So that I can then call this a sigma delta functor. So a sigma delta functor, f from E up to k, is a delta functor such that, and then there's some extra conditions. Firstly, each f delta f has a left adjoint f sigma f going from fx to fy in k. So in any bicategory, we can talk about a map having a left or a right adjoint just by writing down the usual unit, co-unit, and triangle identities. And then moreover, we want to say for each pullback square, I guess of this form, so like D, C, B, A, F, G, U, B in E, the canonical 2-cell so what does it look like? It goes from, I guess, FC, FD, FB, and then here I've got FA and FB. So this seems to be F delta F, and then this is F delta V, and then down the side I've got F sigma U and F sigma G. And so there's a canonical 2-cell there. And I guess I could call this the canonical Beck-Chevalley 2-cell is invertible. Okay? All right, so that's what I mean by a sigma delta functor. And so there are some natural examples of such. I mean, there are heaps of examples, right? But I guess the two ones which I want to highlight is that, so I guess a delta functor E up to cat is an E-index category and a sigma delta functor from E up to cat is an E-index category with sums. So those are not really examples, they're definitions. So that's just what an E-index category is by definition, and that's what an E-index category with sums is by definition. It's just an E-index category where all the re-indexing functors f delta of f have left adjoints, and they satisfy the Beck-Chevalley condition that all these canonical 2-cells are invertible. Okay, so I mean, it's sort of cheating to say that's an example. But I could say in particular, there's a sigma delta functor E op to cat, which sends x to E over x and sends f to f delta f is equal to delta f. Okay? And so that corresponds to the canonical self-indexing of E. And that's a self-indexing with sums always. And so we get this sigma delta functor. Of course, there are many other index categories over E, but this is always the basic one if E has pullbacks. Okay, now the other thing I'm going to highlight is that there's always a sigma delta functor, which I'm going to call eta, going from E op into span of E. Span sub E seems to be the notation I've adopted. And what does it do? It takes X and it sends it to X on objects. And then let's just say with F delta of F. So F delta of F is supposed to be, so F goes from X to Y. So F delta of F is supposed to be a span from Y to X. And so it's this span here. And then the left adjoint F sigma of F is this span here. Okay. So I guess it's a well-known fact that in span, maps of this form are left adjoint to maps of this form. So maybe it's less familiar, but no harder to, well, easier to verify, in fact, is the fact that if you do this, then the Beck-Chevalley condition is satisfied by these maps. And I mean, it's basically just describing what composition of spans is. I mean, it's just basically automatic from that. Okay. All right. And so I guess the theorem, oops. So this is Dawson, Perret, Pronk, 2004, is that eta E op to span E is the universal sigma delta functor out of E, i.e. for any bicategory K, composition with eta induces a bioequivalence between homomorphisms of bicategories from span E into K to the bicategory of sigma delta functors from E op into K. Okay, so I'm sweeping a few things under the rug here. In this paper, they don't actually prove exactly this because they don't consider the whole bicategory of homomorphisms, pseudo-natural transformations, and modifications here. I think they might just kind of consider the set or something like that. I'm not quite sure. I can't quite remember, but I mean, this is really what the result is. No one's exactly written it down in quite this form, I think. No one's actually checked the details of the coherence for these things both being the full bicategories. So in the paper that I'm about to cite, this is checked, but where this is just the category of homomorphisms and icons between those. So icons are identity components, Oplaks, natural transformations, and they make bicat into a bicategory, and then this is just one of the hom categories of that. And similarly, there's a category over here of sigma delta functors. And so that is verified in detail by Charles Walker in the paper, which I'll tell you about in a moment. The other thing I'm sweeping under the rug is exactly what the one and two cells are on the right here, or just the one cells in the sort of reduced case I just mentioned. So there's some kind of Beck-Chevalley stuff. So if I have a natural transformation between two sigma delta functors, then that natural transformation, some of its components turn out to have to be invertible, basically for Beck-Chevalley reasons. But I'm not going to tell you about that. I'm just going to tell you there is a sensible notion of transformation between these things, and you can go away and read the paper if you want to find out exactly what that is. Okay. I should also say they prove some more general thing where these things, they don't take full homomorphisms, they take some even weaker notion of of map between bicategories over here. And again, I'm going to ignore that for these purposes. Okay, so that's span. And so, I mean, in the end, what it tells you is that span of E is obtained from E by freely adjoining, well, I could say span of E is freely obtained from E op by freely adjoining a left adjoint to each morphism such that the Beck-Chevalley condition holds. Okay, so I mean, that's exactly what this theorem is saying. It's saying that this is a free construction of a bicategory with a sigma delta functor from E, which comes to the thing I just said. All right. So now let's do poly E. Okay. So, so as mentioned above, let's take E to be locally Cartesian closed. So definition, a delta pi functor, E op to K, is a delta functor such that each f delta f has a right adjoint. F pi f such that the canonical Beck-Chevalley 2 cell associated to any pullback square in E is invertible. So, I mean, basically exactly the same condition as we wrote down previously. Okay? I mean, I guess you could also say it's a sigma delta functor from E op to K co if you really wanted to, but I prefer not to say that. All right. So the reason I've written down that apparently exactly the same definition as before is because now I want to say what a sigma delta pi functor is. And so a sigma delta pi functor f from E op to K is a delta functor, which is both a sigma delta functor and a delta pi functor, and such that for any distributivity pullback, so remember that's some diagram like this. So I take some map A to B and a map C, so that's F and G, and then I pi F along G, call that V, gives me an object D. Then I take a pullback that has a map down to B, and that map down to B factors through A by the co-unit of the pi G delta G junction at F. Okay. And so the condition is that for any distributivity pullback like that, the canonical 2 cell of the following form. Okay, so the canonical 2 cell, and that's going to be something like this. I've got FA, FB, and so here, what's that? That's first doing a sigma, so F sigma F, and then doing F pi of G to F of C. That should be the same as first doing F delta of epsilon into Fe, then going across via F pi of, seems to be U into Fd, and then going down via F sigma of V into there. Okay, so the point is there's a canonical 2-cell which goes that way. So that is the right way for it to go, because what I do is I take the Beck-Chevalley square for the pi's, I think, and then I I take the inverse of the Beck-Chevalley square for the pi's, I think, and then I flip some things around. Anyway, there's a 2-cell that goes like that, and you want that to be invertible. Okay, so that's exactly the same condition as we had, that we observed with the sigma, delta, and pi functors between slices in any category with pullbacks. Okay, and so we've just formalized that, but now we're viewing these things as landing in arbitrary, in an arbitrary bicategory K. Okay. All right. So again, we can look at examples. And so like before, so remember before we had these examples here. We're going to have very similar examples here, actually, I guess. So examples. So, I mean, okay, let's look at all the things we just talked about. So a delta pi functor, E op to cat, is an index category with products. Again, that's more or less just definition. So a sigma delta pi functor from E op to cat, sigma delta pi functor from E op to cat, is an index category with sums, products, and distributivity. Okay. Whoops. Okay. So let's give a couple of examples of this. So for example, okay, so I guess there's one sort of super important example. So we assume that E is LCCC. So we have an F going from E op to cat, taking X to E over X, and then I guess with F delta F is delta F, F pi F is pi F, and F sigma F is sigma F. Okay, and so we checked very carefully that, I mean, you could say that all the work we did more or less in the first talk was to show that this thing is a sigma delta pi functor. Okay. So here's another example. So let C be any locally small category. Then we have a delta functor f from set op to cat. So this is over set. And I take a set I and I send it to the category C to the I. Okay, so this corresponds to the canonical indexing of any locally small category over cat. Okay, and so we can say when this is a sigma delta functor, a delta pi functor, or a sigma delta pi functor. So this is a sigma delta functor if C has all coproducts, has small coproducts. So delta pi functor if C has small products. And it's a sigma delta pi functor if C has small products small coproducts and infinite distributivity. Okay, so infinite distributivity tells you that in my category C, if I take like product over J in J, sum over K in K sub J of Xij, then that's canonically isomorphic to sum over F, a function from pi J in J Kj, product over J in J of Xj, comma, oh sorry, that should be Jk on the left here. Jk, Xj, comma, Fj. Okay, and so in particular, I mean, if you have a if your category C is a post set, then this is just the definition of a completely distributive lattice, or I guess it's one characterization of being a completely distributive lattice. And I mean, so for a general category, this is, I mean, this is not just a post set now, but you can still require this condition. And so, for example, it holds in set. I guess it will hold in any pre-sheaf topos or in any essential localization of a pre-sheaf topos. And in general, so I mean, one way of saying it is as follows. I can take the free coproduct completion of my category C. Now, because my category C has small coproducts, there's a functor from there back into C which takes those coproducts. Now, in general, if I have a category with small products, then the free coproduct completion will also have small products. And so this distributivity condition can also be stated as requiring that the functor from the free coproduct completion back into C preserves small products. Okay, so that's another way of saying it. And I guess that sort of ties it in with other kinds of properties of this kind. So things like kind of continuity in lattice theory. And I guess there's continuous categories as well, as Andre and Peter Johnston introduced. Anyway, that's nice, right? And so I guess one final example. So, so Val asked about how this tied into kind of logical things. So, I mean, remember, we called this thing the axiom of choice, the type theoretic axiom of choice. And so the question was whether this tied into kind of the logical axiom of choice. And I guess this is the link here. So suppose E be a topos. Don't really care what kind of topos, just an ordinary one topos though. So we have a delta functor, F E or poset taking X to sub X. And so this is always a sigma delta and a delta pi functor. Okay, so I mean, reindexing is pullback of predicates, and then the left and right adjoints are just given by exists x and for all x. And it's sigma delta pi functor if we have in E that for all j and j exists k in kj such that phi jk holds, implies that there exists f from pi j and j kj such that for all j in j phi of jk holds. Okay, so that's just a formulation of the axiom of choice. When I thought about this years ago, I convinced myself that that is the same as what's normally called the external axiom of choice in a topos. But my brain's obviously gone rusty since then. And since there are much more experienced topos theorists in the audience than I am, I'm going to leave it to one of those to tell me if I'm correct or not. Okay, anyway, that's clearly something that looks like the axiom of choice, right? It's producing for you a Skolem function out of a bunch of inhabited sets. All right, but now I guess the most important thing, which, well, the most important example of a sigma delta pi functor is that there's a sigma delta pi functor eta from E op to poly E given by, well, I guess it sends x to x with well, f delta of f is this. I just put I put f in the pullback position, and f sigma of f, I put f in the sum position. And then f pi of f, I put f in the pi position. So what's that? X, y, y. Okay. And I mean, I guess it's a not too difficult exercise to check that actually these things are adjoint to each other. And similarly, it's an exercise which is maybe moderately more challenging to just check that these things then satisfy the two Beck-Chevalley conditions and also the distributivity condition. And again, if you look at it, basically that's just telling you that composition in poly E works the way that you think it works. Okay, when you check what the invertibility of those two cells actually tells you. Okay. All right, and so at this point, the following theorem should perhaps not seem too surprising. This theorem of Charles Walker, who is my PhD student here at Macquarie, and so he proved the version or the equivalent of the Dawson-Perret-Pronk result, which says that eta from E op to poly E is the universal sigma delta pi functor out of E. Okay. And so again, that just says that homomorphisms of bicategories from poly E into K are equivalent to sigma delta pi functors from E op into K. Okay. So, I mean, I guess one particular thing we could note is that in particular, the sigma delta pi functor E op to cat, sending x to E over x, induces the canonical homomorphism poly E to cat, taking x to E over x. Okay. So in that sense, I mean, this just tells you that E, seen as a category indexed over itself, is a category with sums and products, is an index category with sums and products, and its distributivity condition. And then from that, we get this canonical thing that kind of takes each combinatorial representation of a polynomial and turns it into the corresponding operational representation of that polynomial as a functor between slices. So that's kind of nice. All right, I've got just a few minutes left, so I'm going to try and explain very briefly one final view on polynomials, which I'm going to call the Kleisli view. So this is not exactly, but in my head, kind of, this is how I've interpreted the work that Tamara van Glen did in her PhD thesis. In particular, it has this aspect where we talk about this stuff via distributive laws. And so I'm going to just try and explain this view, but I mean, slightly tweaked to fit it in with what we just saw in this last section. So let's define index categories over E to be the category of delta functors from E op to cat. So just the pseudo functors. And similarly, I can define index category pi E to be pi delta functors from E op to cat, and index category sum E to be sigma delta functors from E op to cat. So just vibration or index categories with sums or with products. Okay. So if we do that, then we get, so here's index categories over E. Here's index categories with sums over E. And there's a forgetful there. And similarly, there's a forgetful here from index categories with products. Okay. And the point is, both of these have left bi-adjoints. And the index category sigma over E. Yeah, thanks. All right, so we have that. We have these forgetful functors, and they have bi-adjoints, and they've got kind of very simple or reasonably simple descriptions. Well, at least this someone has a simple description. I mean, I take my, if I view it as a fibration, I take my fibration and I pull it back along the codomain map of the projection from the arrow category, and then I compose with the domain map. Okay, so that's quite simple. And then for the pi one, I mean, it's kind of simple, but you have to, you do the sum one, but you have to take the opposite of your fibration at the beginning and then at the end. So it becomes a bit less simple, but it's not too terrible. And the point is, these are pseudo-monadic adjunctions. So if we write T sigma and T pi for the induced pseudomonads, on index categories over E, we have that index categories with sums over E is equivalent to T sigma algebras, and same for pi. Okay. So then, I guess, fact, there's a pseudo-distributive law between these two pseudomonads. So T pi, T sigma to T sigma, T pi. And algebras for the composite pseudomonad are, well, they're fibrations or index categories with sums, products, and then also satisfying the distributivity. Index categories with sums, products, and distributivity. Okay, so again, the condition is really that the T sigma algebra structure. So because of the pseudo-distributive law, if I take something with products and I apply the pseudomonad T sigma to it, I get something else with products. And so this the condition to be an algebra for the composite pseudomonad is that when I look at the structure map T sigma of whatever our object is back into our object, so we've got a T sigma algebra structure map. That should be something which is a map of T pi algebras. So in other words, taking index sums should be a functor that preserves index products. And that corresponds to this distributivity condition. Okay. And so I think I'm just going to have time to do this. So I'm going to make a definition. So the zero array theory of T sigma T pi, the composite pseudomonad, so this composite pseudomonad is T sigma T pi, is the full subcategory, the full sub bicategory of the Kleisli bicategory, T sigma T pi, on the representables YE in Hom Eop cat. Okay, so the base category is just the homomorphisms from Eop to cat, and in particular I can look at the representables. So as fibrations, these are just the projections from a slice. Okay, all right, and so this is basically the category of, I mean, it's the full subcategory of index categories with sums, products, and distributivity on the objects that are free on representables. Okay, and so I guess the nice theorem here is that, so let's call this zero array theory curly T, that T is actually just poly E. So this isn't quite a proof, but it's close enough to a proof that you might believe it. So why is this? So there's a magical fact, which is that T sigma T pi is a co-continuous pseudomonad. It preserves all co-limits of index categories. And so that means that T sigma T pi algebra, so if I've got a co-continuous pseudomonad on well, just go one dimension down. If I've got a co-continuous monad on a pre-sheaf category, then the category of algebras is again a presheaf category. And it's in fact the category of presheaves on the zero-ary theory. Okay, so this is, I mean, this is basically just kind of the zero-ary version as opposed to the finitary version of the theory of Levier theories. Okay, I mean, you can find this already in, I guess, Gabriel and Ulmer or something like that. I mean, it's older than that, but there's a nice proof in there. So the point is that this category of pseudo-algebras for this continuous pseudo-monad is bioequivalent to, oh, I should probably have an op here, is bioequivalent to T op cat or Hom T op cat. Okay. But we know that the bicategory of algebras, we know that T sigma T delta alg is just is the bicategory of sigma delta pi functors from EOP into cat, right? We just said it's fibrations or index categories with sums, products, and distributivity, which is sigma delta pi functors from EOP into cat. And we know by Charles's theorem that that's equivalent to Hom poly E cat. Okay? And so I guess the dubious thing that I'm going to conclude from this is that T is equivalent to poly E op. Of course, it's a bit dubious because there's some kind of Morita equivalence problem here, right? I mean, just because the presheaf categories are the same, it doesn't necessarily mean that the actual categories are the same. But you can go through by hand and check that if I just take this thing, I mean, I can compute explicitly what the free T sigma T pi algebras on the representables are, and then I know what, and then I can describe maps in the Kleisli category super explicitly, right? Just because I'm homming out of a free thing on a representable, and so I use the freeness and the Uneda lemma to tell me what the maps are, and they turn out to be exactly the polynomial diagrams, and the composition is the composition that you want, and so hey presto, you're done. So although this isn't quite a proof, the result is in fact true, and I guess I think that's quite a nice way of looking at polynomials, which is, I mean, again, there's a question of how that's related to the Koch and Koch presentation of them, and I don't really know about that, but I think that's a nice place to stop. So thank you all.
Great, thank you, Richard, for those excellent 3 talks. Okay, so people can unmute themselves and ask questions.
I have a question.
Yep.
To Richard, yeah. That's very interesting. If you consider what you call category K together with these functors F sigma and F pi,
yeah.
In some sense, it looks very much, without the distributivity condition, it looks very much like an upper doctrine in a sense of Levier.
Yes, that's right.
So in some sense, one of the big difference between an upper doctrine and this kind of algebraic structure is that in an upper doctrine, you don't have any distributivity condition.
Yeah.
So I wonder what happened to this theory when you kind of drop or you weaken the distributivity condition.
Yeah, it's a good question. I mean, you can always construct I can start with my category E, and I can freely adjoin left and right adjoints for each morphism that satisfy the Beck-Chevalier condition, but not the distributivity condition. And I don't know what you get if you do that. I mean, it's going to be bigger than the bicategory of polynomials, Because I mean, your maps aren't going to have this nice normal form anymore. You might have to like take kind of strings of arrows potentially.
Yeah. Well, that's somehow what makes it interesting, in the sense that if we think of first order predicate logic, it's an upper doctrine, and a first order statement is a rather complicated statement with you cannot always put the string of quantifiers in some kind of normal form, like maybe sigma followed by pi, because there are no rules. So the complexity of first order logic comes from the fact that you don't have a general distributivity law.
Yeah.
Right. So in this sense, the complexity of a system where there is no distributivity law is something very interesting, because it reflects the natural complexity of first order logic.
Yeah, that's right. That's a very nice point. Right, because I mean, it'll somehow this is somehow encoding in a very abstract way the kind of the sigma and pi hierarchies and things like this, right? Very interesting. Yes, I mean, so maybe it's worth trying to, even though it's going to look horrible, maybe it's worth trying to work out what this bicategory would actually be.
Of course, for in all these theorems, you have to suppose that the base category E is locally cotangent close, or something like that, right?
I mean, probably not for the distributivity thing. If you drop the distributivity, then I don't know that it's particularly important. I think you could get away without it, because you only need the locally Cartesian closed in order to express the distributivity condition, really. So I think you could,
of course.
Yeah. So you could get away without it, I think.
Okay.
Okay. Thanks.
Thank you. Yeah. Thank you. Nice talk. Very nice talk.
Thank you.
Okay, I think maybe Nicola was next.
Yeah, thanks, Richard. Just a question: does the work that Ross Street has presented in the other day link in any way with what you're doing? Can his description also be used of polynomials to characterize the two cells?
Yeah, I mean, I think so. Ross says it's they're just span morphisms. So it does really become quite straightforward in Ross's setting as well.
And what about the universal property?
No, that's a good question. So I mean, Charles did this, and then Ross did his stuff later. I kind of let Charles get on with this stuff because he's incredibly competent. So so I haven't really looked at it myself since, not since Ross has started doing this other stuff. So it might be worth going back and seeing how they match up.
Okay, maybe I think Brandon was next.
Thank you, and thank you for these talks. I'm wondering if you could maybe say a little bit more about why you call this the zero-ary theory. I know you mentioned finitary by comparison. Could you just maybe say what the difference is, or if there's like an n-ary theory?
So zero is here in its role as a regular cardinal, I guess. I mean, that's not normally how you define a regular cardinal, but I'm including, so, okay, so you can talk about Levier theories for any regular cardinal kappa, which means that you have kappa small limits. You have a category with kappa small limits, and then you look at functors preserving those kappa small limits into set. Okay, so the nullary version of that is I've just got a small category and I look at functors from there into sets. I'm just looking at pre-sheaf categories. And in the same way that you can associate to any finitary monad, say on set, a Levier theory, such that the models of the Levier theory are the same as the algebras for the monad. I mean, you can generalize that not just from set to other categories. And similarly, you could look at monads that preserve not just filter colimits, but all colimits. And then you can try and give a characterization of the category of algebras of those monads in terms of some kind of theory. And in particular, if I look at a co-continuous monad on a pre-sheaf category, then I can present the algebras for that co-continuous monad as themselves a pre-sheaf category, which I can think of as the category of models of some theory, where the theory is the thing that I here called the zero array theory. So I don't know if that clears it up a little bit, but that's the idea basically.
So the zero sort of indicates that you don't need to impose any kind of limit conditions on these models, which is why you get that it's appreciated.
It indicates you're looking at monads that preserve all limits, all colimits that commute with the empty class of limits, which is all colimits.
Thank you.
Okay, looks like we have one more question from Valeria.
Yeah. Hi, Richard. Thanks very much. That was really very enlightening in lots of ways. But the question is mostly it's mostly a comment over Joel André's comment, because, you know, I was hoping that you were going to tell me the connection between this version of polynomials and Tamara's kind of and Moss paper, where they actually have some sort. I mean, what happens? André was saying that there is no that you cannot put the quantifiers in this shape, but of course you can if you use the dialectica, right? That's exactly what you do, is to transform quantifiers in first order logic into a big existential followed by a for all. Mm-hmm. So I was kind of trying to understand better how you connect that to the paper that I don't know if you've seen in Leaks 2018. Have you seen that one? By Tamara von Glen and Sean Moss.
I haven't read it. I should give it a look. So that's about dialectica, right?
That's correct, yeah. So that was the asking was exactly how the dialectica kind of connects to this version of Poly. And I think it, you know, from what you're saying, it looks like it's a Poly over Poly or some sort of thing like that, because you do this opping and opping again, and then maybe that's how you end up with what the dialectica gives you in terms of quantifiers. I don't know, but thanks. Right. I mean, I thought you might have something else to say about that, but if you haven't seen the paper, maybe you haven't yet.
Right. I mean, I guess the other related thing I know is this paper by Peter Hofstra about understanding the dialectica monad, sort of in terms of exactly these completion processes. But I don't, because I haven't seen this this paper of Tamara and Sean. I should, I guess, have a look at that before I try and say anything further about this. But yeah, thanks for the reference. I'll definitely give it a look, because I mean, of course, there is obviously there's a lot of relationship between this stuff and the dialectica stuff, but I guess I haven't delved into that too much myself so far.
Thank you. Thank you.
Thank you, Valeria.
Well, thanks again, Richard, for these 3 tutorials. We can now finally thank you. And I guess we'll see everyone tomorrow. Same time, same place. See y'all.
If there are not more questions.
I don't think there are more questions.
Thanks, Richard.
I think Andrea was asking if he could ask another question.
No? Oh, I didn't hear that.
But maybe not.
So any more questions? Okay, well, we'll see everyone tomorrow. Thanks again, everyone.
Thanks, Richard. That very nice talks.
Thank you. Thank you.
Thank you, Rachel. Bye.
And
Good night.
thanks for taking so many midnight slots. That's a good way to keep us awake.
Good to see you. Bye.